Okay, welcome to today's feature on Interact, on our Interact experiment. I'm going to show a couple of slides actually about the purpose of the experiment. We have some audience here in the room and some audience watching online. So I'm presenting on behalf of my team the Interact mission, which is taking place today for the very first time. And actually Interact is a part of the Meteoron suite of experiments. So in Meteoron, we actually have the scope to develop robotic technologies that allow robotic control on a planetary surface from space. That's why we have a space station up here and a planetary surface. And if we want to send humans to Mars, for example, we have to land them and launch them, which is basically impossible with the technology that we have right now. So we decided to come up with an alternative where we propose actually having humans in the orbiting station and the robots on the surface, and the humans project their skill and capability into the robotic system to do human-like tasks through the robot on the planetary surface. We have an orbiting station around Earth, so we use the space station to actually validate these technologies on Earth with the robotic system that we have here behind me. So we conceived in the technical directorate of ESA 3 projects basically for developing these technologies. The first one is Haptics 1. We flew Haptics 1 in June last year on ATV5 in a very short development schedule. We actually built the hardware within less than 12 months. We put a small force-reflecting joystick with a real-time computer and a tablet PC that we built here in ESTEC, actually in-house, on ATV. We flew it, and in December, Butch Wilmore was the first person ever to actually perceive force feedback in space. And I'll outline a little bit what we did there, because it introduces what we do today. After Haptics 1, we actually did Haptics 2, which was using that same joystick and the tablet PC to make a space-to-ground telerobotic experiment in which, for the very first time in the history of spaceflight, we actually controlled a robotic system on the surface with force feedback delivered to the space station. As a part of Haptics 2, we did a handshake where we could actually shake hands between the astronaut and myself in this case on ground. We did that 2 times in June and in August this year. So for Haptics 2, we use 2 communication links. One is a direct one, which we will be using next year. It's a link that DLR in Oberpfaffenhofen has developed and operates jointly with partners in Russia. And we did already test via a satellite link, which is called the TIDRIS satellite system, the data relay satellite system. And this relays signals basically from the space station up to geostationary orbit and down on the surface to the US, and from the US to Europe, where we picked up the signals. Now today, we actually continue the series of experiments with our first really big experiment in which we do an end-to-end task. So this is a continuation of Haptics 2. Haptics 2 also identified the network, and we did some network characterization to measure the delay, which we need to actually adjust the control methods that we're using in Haptics in Interact. So in Interact, we are using this robotic centaur here to actually do a pack-in-hole task. Now, a pack-in-hole task sounds simple, but it is actually a simple form of a connector mating, which has a mechanical alignment requirement that is in the sub-millimeter range. So what we're doing here today is actually a 150 micrometer precision assembly task. And we are not doing this from here. Andreas Mogensen will do it from space. So here we see Butch Wilmore during the Haptics 1 run in December, 30th of December. As he operates our joystick, you see the joystick here. It's a 1 degree of freedom device. It's this box which holds a real-time computer that we developed here in ESA with a real-time operating system that we developed. It's based on a Linux kernel that has a patch, an RT patch. The joystick is only coupled to the power source on ISS and to the tablet PC, which is here, which is a Dell Latitude tablet which we qualified. And the tablet actually runs the graphical user interface. That's actually something new in the space station that normally is used to having astronauts read PODF procedures, which is a PDF file specifying step by step what the astronaut needs to do. What we did for the very first time is actually have a touch screen like your app on your iPhone, which actually automatically guides the astronaut through the procedure, which is really nice because we can update this from ground and we can directly control the astronaut, basically what he does in terms of the experiment. So in Haptics 1, Butch did actually a set of 7 protocols, and the protocols were all aimed at qualifying and identifying the human performance related to the motor control system of the human and the hand-eye coordination, the neuronal configuration in microgravity. So protocol 2 and 3 are, let's say, hand-eye coordination tasks where the astronaut needed to track a signal on the screen, and once he tracked it with a position input to the joystick, another time he tracked it with a force input to the joystick. But for today, more relevant are protocols actually 5, 6, and 7, which are called discrimination tasks. So here the astronaut gets a stimulus, for example a force or a stiffness stimulus on the joystick that is rendered, and he has a screen that looks like this where he can select between stimulus A and stimulus B, and afterwards he needs to rate which one was the more intense stimulus. So in stiffness discrimination, which was protocol 6 of Haptics 1, he would probe different stiffnesses that are rendered by the joystick, and we would vary the changes to the stiffness between the stimuli and thereby find out what is the minimum difference of a stimulus for stiffness that he can actually perceive in microgravity. Nobody has measured that ever, and we got some quite interesting results from this. I'm highlighting this because today we will go in more detail in this stiffness discrimination tasks, because the astronaut Mogensen will actually need to do an experiment like this that is teleoperated from space to ground. So by this we can directly infer whether the teleoperation controller or the human performance in microgravity is responsible for changes in the stiffnesses that humans can perceive. Now, why is it different or important actually to know this? Well, hand-eye coordination and neuromotor control is very important to do human tasks. So if we want to manipulate objects, to insert connectors in sockets, we are heavily relying on a daily basis on our motor control system. And we know basically by these measurements whether this performance increases or decreases in microgravity if we want to do future control tasks from there. So this is a very simple video of haptics actually, where you see here the stimulus that he can select and then actually the one that he rates. And we go through trials, so there are actually 200 trials in Haptics 1, and there's variations, certain constant variations of the stimuli. So after a while we know exactly whether he's actually guessing or not guessing these differences. So this will give a curve that actually looks like this. You see here basically a base stimulus level of 1 Newton meter per degree. It corresponds to a spring that you can press. And then you see the differences here of 40% going down to 5%. And here you see actually the number of percent, so the percent of correct answers. So you can see here that for a 40% change in a stiffness, he actually correctly identifies that to 90% of the times in the ground case. So the triangles are ground, the round ones are actually the first in-space measurement that we have. And we saw something quite interesting here that shows actually that the perception seems to increase in the space environment, which is very unexpected. So we have for now only 1 astronaut that actually did that task. We have 5 more astronauts to do it. So we are very excited to find out actually what this effect is in the space and microgravity environment. Well, Haptics 2, I mentioned, was a bilateral control, which means a force feedback control from space to ground. And you see here the setup that we used in August with Kimiya Yui, JAXA astronaut. You see here the live feed from the ISS and the astronaut interacting with the joystick while we are shaking hands here via the joystick on ground. As I said, we did some technical measurements first to identify the link, to characterize the link. And then also we did some force feedback control tests for 2 different control methods that we have developed in ESA and jointly with the Delft Robotics Institute. This is how a measurement of the latency looks like. And you can see here that the satellite link had about 850 milliseconds of time delay. which really for the control people is a lot. And if you imagine, this is not like controlling, let's say, a robot on Mars, but this is really an interactive coupled control, much like driving a car. And imagine if you have, during car driving, time delay, this is very bad. Actually, it makes it very hard. So it was very important to know exactly those metrics. Well, the handshake was, of course, the more PR representative test here. But it actually also resulted in some identification and validation of our control methods. You see here basically the recording from the June session with Terry Wirtz, and it was very extraordinary to actually feel his handshake and actually feel his handshake before I could see it on the video screen, because the video from space station is delayed by about 3 seconds. So once we had actually the force feedback link established between space and ground, we could communicate with the astronaut in a different way, which was quite odd, in fact. So I could give him signs through our video feed, which was incorporating much less delay than the official ISS video feed. Okay, I will go forward and let's have a look to the Interact experiment, to the science protocols. So basically in Interact, we have 2 protocols, Protocol 1 and Protocol 2, that we are testing today. In Protocol 1, we are repeating the stiffness discrimination tasks that I have just explained between space and ground. So on ground, we have a setup which is basically the flight spare of our force reflecting joystick, and you can see that over there in the room set up. And here you see another system, which is a spring simulator. So it's a mechatronic device with another real-time computer and a force torque sensor that can very precisely render stiffnesses of different amounts. So what in this case Andreas Mogensen will do, he will select from space a certain stiffness to be rendered here, he will probe it, and he will do again the paired comparisons, which we call a 2 alternative force choice test. And the link will go again through the satellite connectivity, and I will outline a bit more in detail later what that actually entails. So this will really answer the question, which human skill is projectable on a planetary surface? So what sort of tasks are we able to do with this type of teleoperation and telerobotics in the future for future exploration missions? And the test levels are actually identical to the ones that we used in Haptics 1, so we get an identical data set that exactly identifies what is the contribution of the microgravity environment and what is the contribution of the teleoperation and the control method that we use for this. So this is how it looks like for Andreas. He has a graphical user interface here which shows a video stream that is live on the setup, and you can see that in the back of the room. He will use the wand-off from the space station, and he sees these little buttons here, green and blue, which allows him to select the stimulus, and then he actually registers the one that he perceives as the more intense, or in this case the more stiff one. And we actually will cycle through 120 repetitions, which involve 4 stimulus levels. So all the stimuli are randomized, and every stimulus is tested against the reference. And on ground we have the setup here, which is actually involving 2 computers. So there's a dedicated computer for the spring simulator and a dedicated real-time computer in the force joystick on ground. So it's actually 3 different computers roughly that interact here together. We're using 3 data channels for this experiment, roughly. So the astronaut actually selects the stiffness set point and the joystick position by really giving input to the joystick. The joystick on ground follows, and essentially he's receiving real-time video. He's getting the estimated stiffness back from the slave joystick and the contact location. And this is because we're using a very specific control method here, which is called model-mediated control. In this sort of time delay with under 850 milliseconds, you cannot do a direct bilateral control. So we have developed another method that makes use of these stiffness estimators, and he will ultimately also receive force feedback on the joystick to actually verify the spring and then rate which perceived stimulus is what. That's the more scientific part, let's say, of today. Now, the end-to-end experiment is Protocol 2, actually, and you see behind me on this side, for the people in the room, our Interact Centaur parked. You can see it here. It's a robot that we developed at ESA again jointly with the Delft Robotics Institute. And Centaur is a mobile platform. It's about 450, 500 kilogram rover with two 7-degree of freedom impedance-controlled arms, a head system with cameras and multiple cameras that allow actually situational awareness for the one controlling it. So Andreas, in this case, will have the task to actually insert a peg in a hole, and the peg and the hole have a mechanical tolerance of only 150 micrometers. He will control this from 400 kilometers in space, traveling at a speed of approximately 28,000 kilometers an hour. So how does this setup look in a more specific way? We again use roughly 3 data channels, and in this experiment we actually use a new communications technology. We don't use point-to-point connections, but really data spaces and data-centric publishers, which is a protocol DDS, a data distribution service. So we have here on the ground side a data distribution service running with multiple publishers and multiple computers, and also on the space side. Between space and ground, we are actually syncing both systems and also ensure that we are robust to communication dropouts, which can always happen. Even the Tetris constellation has certain times in which there's no connectivity, and we do not want to be constrained to planning our space operations in a field where we have connectivity. So we implemented that by means of status and control words to be always in a good state with our software, both in space and on ground, no matter what the link is. So the astronaut receives a live video feed here on his graphical user interface, and this one is the screen he uses while driving the robot. He can select from 4 different cameras, actually. The head camera, a front HazCam, and a back HazCam, and a tool camera. And he will, of course, do the robot arm control via the GUI. So we have widgets in the GUI that allow him to actually drive or to manipulate the arm, depending on where he is in the experiment. And we leave really entirely to his choice what he does actually with the system. So if he wants, he can drive against the wall. We will let him do that. We hope he won't do that. He will control the head, basically the head of Centaur with its camera, the platform for driving and steering. And there are some videos on YouTube, or later I will show some videos of what the platform can do. We are projecting also a virtual reality kind of augmented reality overlay onto the video feed in order to help him do this task in a better way. So you see here actually some colored items, and they will show the commands that he's actually sending while the time delay is still taking time to actually bring the command to ground. We also give him some intended parking positions on the taskboard. The taskboard you can see over there is very small, and the robot arm workspace is also relatively small, so he needs to park with a certain accuracy, which is constrained by the VR overlay, so he gets real-time feedback from this. All the status is reported actually, so there are several widgets for navigation and distance to taskboard and the heading in the room to help him orient himself inside the room. And ultimately he will use, again here also with the same or similar control method, the stick in space to actually control the robot arm for the insertion task. So it's a really full 6-degree of freedom task, and he will receive force feedback from the Z-axis insertion on our joystick. Now, very briefly about the control method. Model-mediated control essentially allows to feed force feedback from a robotic system to a joystick over very long latencies. In fact, up to infinite amount of time. So this would work also with 2 seconds or 3 seconds of time delay. From 3 seconds, humans have really problems in doing hand-eye coordinated tasks. So it doesn't make sense to use this in much longer time delay situations, but it would bring us from here to the moon, for example, to do force feedback teleoperation in environments that are suitable. So roughly, without going in detail, what it does, it relates a model of the slave side back to the master, thereby cutting the time delay in the actual control method, and then the master interacts with a model that has been online estimated at the slave side. So the estimation takes place within the robotic system, so we do not need a priori knowledge of the environment. So this works in unmodeled environments. I want to go in a bit more detail about the satellite communications and the overall setup of the experiment today. So communicating between ISS and ground is not straightforward. You see astronauts doing Twitter feeds and blogs on websites. Well, very often this is done by ground staff at NASA, actually, because the ISS doesn't have internet as we know it. It's a highly customized system with mil-bus systems, partial networks, and so on. So there are in principle two ways to communicating with the station. One way is direct, and there is an S-band link called Contour 2, developed by DLR in Oberpfaffenhofen, still operated by Russian colleagues of Energia and Roscosmos. Now this direct link has a round-trip time of about 2 to 4 milliseconds because it's 800 kilometers to send a signal up and down, which you need for the bilateral control. The downside of this link is you only have this link once ISS passes over your ground station, which is about 7 minutes at most, or 7.5 minutes. If you subtract from the 7.5 minutes the time to connect, establish connection, the singularity of the ground antenna during the highest altitude, then you are ended up with about 2 times 3 minutes, if you're lucky, of experiment time, which is very little to actually do robotic science. So the alternative that we chose for today is actually go via the Tetris communication system, and from there to the United States, to a ground station, and from the United States to Europe. So this is about 36,000 kilometers up to geosynchronous orbit, again down to the United States, and from America about 10,000 kilometers here to the Netherlands into the test facility at ESTEC. This gives us a distance of about 140,000 kilometers where the signals travel for our tests today, and about 850 milliseconds of time delay. And the big advantage of this link, despite the disadvantage of having significant signal lag, is that we have coverage of about 90 minutes or even longer, depending on the constellation with respect to Earth. So let's have a look in detail in the computers and processes involved in this experiment. So we have ISS with our joystick at 400 kilometers above surface, and our joystick has basically a real-time computer and a tablet PC. If we look at the network in the space station, it actually looks like this. And you see it's a very complicated network setup, and we had to find our routes through this network to actually get from the Columbus module, which is here, to the NASA IPAC, which is actually the communications interface to the Tetris satellite system. So we worked together with NASA, Johnson Space Center, Marshall Space Flight Center, and experts at Boeing to actually reconfigure the ISS networks to allow routing our signals from here to there, which was not by default the case. So going through this line, we actually are connected via certain switches and routers to the N2 Node 2 edge router, from there connected to the US laboratory edge router, and from there to the IPAC. So all of these computers needed to be configured properly to relay our data that flows in both ways through this system. Well, from here we go up to the Tetris system, which involves, of course, computing in the satellite, which is a satellite repeater. And from there it will go down to White Sands Ground Station in the United States, in New Mexico. There are, of course, multiple computers involved, related also with authentication and so forth. From there, it goes to HOSC at Marshall Space Flight Center. From HOSC, it goes to Johnson Space Flight Center. And from there, it actually goes to GSOC in Germany, which is the European Ground Support and Operations Center. From GSOC, we are going to the European facility here in ESTEC. And from ESTEC, we go to our Interact test site, which is here. And each of those links here involves actually multiple computers, makes use of the IGS ground operations LAN and all the security authentication related to it. So here in the room, we actually are connected to an MPCC authentication terminal, which actually authenticates our streams. And from here, we are on what we call the Interact switch. And from here, our actual ground system starts. So this is a rather complicated communication setup, but in fact, for us scientists, in fact, it is also important to get really good data measured. So we are doing real-time control between here, and we want to be able to post-process our data. So this is not it, because we want to have our data in the same time base. We actually added a link to GPS on the space station to actually record the GPS time via NTP protocol, and also connected to the GPS satellites, our ground facility, so we get the same GPS time basically on both facilities, which would allow us to really correlate our data well, to do the MATLAB plotting for the scientific publications and so forth. Our robot looks like this, roughly. Well, we have a 220 volt power system in there, and batteries, and a power distribution and safety system. Where we have vision cameras in the head for teleoperation. We have on each robot arm Cartesian force torque sensors and grippers, which measure in all 6 axes the forces and torques, which we use for the Cartesian impedance control. We have forward and backward HAS cams, which actually look at the shadowed area here in front of the chassis that cannot be seen by the head camera for driving. And we have about 7 computers on the system and different routers that all run processes in parallel. So let's have a look at, in more detail, our test setup that we developed here at the Telerobotics Lab. We have our ops consoles, which is basically consisting of a voice loop system, which you will be able to see later on over there on the desk, which allows us to talk directly with the astronaut during the crew, with all involved positions in the flight operations, that is call flight or Stratos, all the people supporting our experiment. We have multiple operation consoles here, which show the visualization of the timeline on board, the planning on board, because we need that to be always updated for our experiment. And then we have the interact switch and authentication that actually connects to our system. What we need in here as well is in fact a space-to-ground network simulator, because we of course need to develop all the software that is running on the space side on the ISS. So we need to test this also from here. So we have a space sim, which is actually right behind the screen of a joystick, which is tablet PC and one DOF, actually located here in this room, that can act as an astronaut console for us in order to test the readiness in a real communication scenario, as would be with the actual Tetris system. Well, from there, of course, we are connected to our Protocol 1 ground facility with the joystick with its computer and the spring simulator with its computer. So we have 3 computers running real-time processes here for Protocol 1. And at the same time, we are connected to our robot, to our Centaur, which runs 8 computers. So for the left arm, there's a robot controller and proxies, as well as for the right arm. And there's an avionic computer, camera controller, navigation computer, and the Centaur router that makes sure all the systems are properly addressable. Of course, we also have in the test site a measurement system, which we use for ground truth measurements, and you see this in the back of the room, which actually measures the position of all the robot and the taskboard and the pack for post-analysis, and actually also to aid the virtual overlay for the astronaut. Now, this is about 10 programs running on the robot with 10 publishers and actually multiple threads running in parallel on the computer. We are also connected to the GPS time in order to synchronize all the computers with GPS time for the post-processing that I explained earlier. And in total, this is about 19 computers that are involved that run processes in real time, with about 25 data publishers, and I assumed it's about hundreds of processing threads that run in parallel for these experiments. We developed actually all of those software programs here in-house, and we use extensively model-based design, which we have developed here also in the lab, which are basically cross-compilers and autocode generators for the control parts, but not for all parts in the experiment, of course. So this is just some video we recorded quite a while ago, actually, when we started integrating the robot, and we showed that for the Delft Space Institute opening, and it just gives you a little bit of behind-the-scene B-roll material of the robot. We integrated here in our what we call dirt room, which is our integration room behind our labs, clean room, where equipment will be assembled that goes outdoors. And here we are taking actually Interact for a first spin. It didn't get its proper paint job done at that point. And we can navigate through the narrow corridors at ESTEC, which proved very helpful. But later in this video, you see some sequences how the robot also maneuvers outdoors. Luckily, we took a decision in summer to actually plan for testing this test in September indoors. And well, we were proved right. It's raining dogs and cats outside since days. The platform is actually going to be weatherproof. The shell is already weatherproof. We are still working on weatherproofing the arms, where we have industrial design students from the Faculty of Industrial Design in Delft working on. And here you see the first spins. And if you look at how Interact actually manipulates through these obstacles here, you see that it's very well compatible to go in rough terrain and outdoors. Here we just tested like the climbing capability, and bear in mind it's about 500 kilogram platform, and we couldn't actually find any terrain at ESTEC where it wouldn't maneuver through. So we have been in the sand pits of the golf course, I shouldn't say that loud probably, and in other places on the golf course and in the dunes. And here you see that it's driving entirely autonomously. It has autonomous power for about 2-3 hours of operations for its computers, the platform, and the robot arm controllers. You see here what we call the grab mode, so it can go sideways if all the wheels are inclined. It's a four-wheel driving, four-wheel steering platform, so it's very versatile. For today's experiment, because it's the first time, we actually constrained the platform to spot turns and straight line segments for the astronaut, to not overwhelm him with possibilities for control. And of course, a very well test is always steps and little stairs to drive over, and you can see here the system has no problems with that. I think it's gonna come up again once. It can actually drive pretty fast, up to 20 kilometers per hour. And we constrained it now to about, I think, 3 or 6 kilometers per hour for this experiment. But we were all a bit bored of very slow space robots, so we decided to make it a bit faster for these interactive types. Let me see, I think this is another role, just explaining the modes of the robot that it can have today in the facility here. So here you see Interact in its final paint job actually. Media started comparing it with Wall-E or number 5. I'm not sure which one looks closest to it. This wasn't intentional though. It nicely shows the ESA and TU Delft blue. And you see here Interact on a spin, actually doing some of the motions it will do inside here. You can see that it's fairly fast. Here actually he's holding the pin in its hand already, and the sideways, the lateral motion and the turns you can see here. Okay, you'll see more of that today, so I'll move on. One feature that I would like to outline is we are not using a stereo camera for the operator to do the sub-millimeter precision task. Because we did some research on vision and stereo camera vision and monoscopic vision, and actually from those research we did, it showed that there are a lot of cues available otherwise that actually make it feasible to do depth perception without stereo vision. For this purpose, we have here a laser in the tool that actually projects a small red dot, and you can see that here on the image on the taskboard. And this information actually is enough for humans to estimate the distance and the spatial alignment of the tool towards the taskboard. It's like your shadow that you're casting when you're approaching something. So it saves a lot of bandwidth actually on the space-to-ground link. And in fact, stereo vision didn't prove to be really helpful in making this task better. Okay. Couple of slides now. I will just run through the GUI that Andreas will see. And so his first task actually, and this is the graphical user interface he will see on the tablet from now on. So first he will see the video feed here and of our moon environment. He can select the cameras, and his first task is to actually identify the taskboard in the room. So he can use the control widgets here, he can change the scaling of the control, and he sees predictive overlay on those widgets here in the GUI controls. So after he has identified the taskboard, he actually needs to register the taskboard by pressing a button here called Place Target, and from that moment on, the target will be tracked in the widgets down here. Following registration of the target, he has to drive there. And you see here the target basically shows the alignment with the camera and the robot here roughly in front of the robot. He sees the distance of the robot to the target. And here you see the augmented reality overlays projected into the video stream in real time. So what you see here is in yellow the actual footprint projected ahead of the robot. So he knows always in reference where he is. And in white you can see his predicted command. So we took that screenshot after pressing forward for 1 meter and taking the screenshot. So this one will align automatically with the yellow one once the robot has actually moved. And the green target here is what he actually needs to align the robot with. So that's a challenging task. He needs to do very fine manipulations in the room to actually align the robot nicely to the taskboard. Once he did that, and this will look like this in his screen, so the alignment has been successful, automatically in the GUI there is a button enabled, which is actually disabled before. So if you look again the screen before, this button is disabled. And this is just an example how the automatic crew guiding works in the GUI. So the GUI has knowledge about all the states of the system. Once he's close enough, this button enables so he can press it. So he doesn't need to be trained when to press which button. It's intuitive in the GUI. It actually, after pressing, guides him to this screen, which is the tool control screen. And from there, he will need to manipulate the robot arm to actually do the 150 micrometer tolerance mechanical assembly. So he will use the right robot arm to align it here to this hole. He can use a rough alignment feature in the GUI, which will actually bring the robot arm close to the hole. Of course, all the measurement system have inaccuracies, so this alignment can never be perfect. This is why he has a widget here for the robot arms to fine control, and he can change the step size on the linear and rotational controls of all 6 degrees of freedom of the robot to fine align it here into the hole. So the next step is actually now in the tool camera view to actually align the pack to the hole. And here you see the interesting feature of the laser dot, in fact, that shows when it's not aligned, the laser is visible, because he needs to insert it in a hole. Well, it's not really a black hole, but in the video it actually is. So once it's fine aligned, actually the laser disappears, the light disappears, so he knows his alignment is good. And he actually can start using the joystick for the insertion task. The task is finished once he managed to insert the pack into a depth of at least minus 40 millimeters. So he has to insert the metal pack into the metal hole at least 4 centimeters deep, thus not tolerating any rotational misalignments anymore. And automatically a small LED will indicate that the connector is basically connected in the taskboard. And from there he can actually press finish and the experiment run will be finished. We are of course recording all the forces on the ground sides and the space side for the post-processing. Okay, well, this is protocol 2. It sounds fairly simple to do, but you also see all the systems that are involved, all the communications involved, all the dropouts of communication that can occur. So fingers crossed still, and we hope that our system is really robust to the extent that we expect it to be. I just want to outline the people who have actually worked on this. In fact, I almost didn't do anything on this. Technically, I was only doing some part of the robot control to do the alignment. But really the technical work, I want to highlight the work of Thomas Krüger. I don't know, Thomas, where are you? Maybe Thomas, you come and wave briefly. Well, Thomas has been responsible actually for a lot of things on the experiment related to the space-to-ground communications, all the setup of the network simulation, and of course Thomas is behind the wholly autocode generation tool that we use in the laboratory. He has been stepping in for me for a lot of the organizational items, also with NASA and with Johnson Space Center, and making sure that the link works. So I hope you have just done some network testing right now. How does it look like? We're good to go. Very good. Very glad to hear that. Okay, thanks, Thomas. Then we have Joao, and this is really random. There's no prioritization. Random on the screen. Joao, where's Joao? If you can just stand up. Joao Rebelo. He has been a PhD student. Now he's Dr. Joao Rebelo since a couple of months. Joao made his PhD also in the laboratory on telerobotics and bilateral control. And for Interact, Joao has taken care of the graphical user interface and also of the robot, the platform control. So a lot of work has been also contributed on different systems by Joao. I want to show Jan. Jan, if you want to get up. Jan Smiszek. Jan is still a PhD student in the lab, wrapping up his PhD thesis in the next couple of months, I believe February, March timeframe. And Jan has worked extensively on the 1 degree of freedom spring identification setup, on the model-mediated control that we are using, so mainly on protocol 1. And actually, I should not forget, Jan has done a lot of work in integrating the Interact Center and supervising the integration works that we did also with students on the hardware side of the robot. Well, Alex joined our team. Alejandro Hernandez from Mexico. He joined our team as a software engineer, I think a year ago, roughly. It feels longer. And Alex has been working mainly on software, on the space GUI and the ground GUI, and the communications between the two GUIs in space and ground to ensure that any loss of signal is properly captured and actually not leading to any degraded software performance. We have Eloise Matheson. She has been a YGT at ESTEC and now is part of the team as a contractor, and she's probably going to do her PhD sometime. And so Eloise has worked on the robot control, on the robot arm control, on the center, and actually supervises today all the activities on the robot. So she'll be in charge of the robot system to make sure that all the robot communication systems, the arm controllers, the platform controllers, and everything works. And she has done a lot of work on identification of the Interact Center, actually. Then we have Emil. Emil is an industrial design engineer. So Emil is our wizard when it comes to human-robot interaction. So Emil has worked extensively on the graphical user interface, actually how to present information to people. And Emil makes sure we're getting the live stream and all the coverage and all the media today. We have Manuel. Where's Manuel? Manuel should also get up. Manuel Eiple, a PhD student also in the laboratory and also with Delft University of Technology. He started his PhD recently, actually on a different topic. He will look at the next generation of robotics, of actually soft robotics. But on this project, Manuel has worked extensively also on making sure our software works, both in the space and ground GUIs, and actually also the communication system with respect to ISS connectivity and ground connectivity. So Manuel will make sure today, if anything goes wrong in the space part, to actually, he has this unique skill of doing predictive typing over time-delayed SSH terminals. So Manuel will make sure if something goes wrong in space, he will be logged into the computer and fix this in real time. And he actually saved our haptics 2 operations last time because we had a wrong configuration on the network, which was not on us, but Manuel actually fixed it in real time during the ops, so we could actually complete haptics 2. We have Frank van der Hulst. Where's Frank? Frank is also there. Frank is a mechanical engineer in the laboratory. So Frank is basically responsible for the entire mechanical setup that is involved with the experiment. That is the rover, the task board, and all systems that you actually see visually is going through Frank's hands. Stefan here. Stefan Kimmer should come here, also say hello. So Stefan Kimmer is the vision expert that we have in the team. Basically all video feeds from the robot, all the real-time video, all the low bandwidth video is actually developed by Stefan. Stefan is also a PhD student from Delft University, also in the laboratory. He makes his PhD on predictive interfaces and predictive control. So also the virtual reality part and the overlay, the augmented reality overlay, has been taken care of by Stefan. So Stefan today will make sure the astronaut receives video from ground in real time and overlay. Then we have two master students currently, Nikki Moll. Where's Nikki? Nikki works actually with Jan on model-mediated control and on perception of model characteristics for teleoperation, if I may explain it like this. And we have Matthijs Damen, who is also a master student at the lab that you see in the back. And Matthijs works actually on path planning on the robot and non-holonomic control of the system, which we'll use in follow-up experiments probably. Then I should also say we have a lot of people here, Case and Kevin, that help us actually with the experiment and with the security. I'm sorry that I didn't put all of you in here, but I'll mention more at the end of the day. And actually I thought it would be a good idea to also show the companies and the products we are working with, just to show a little bit the amount of people involved actually in this experiment. And now, of course, I will not go in detail about all of them. Of course, there's KUKA for the arms and NASA basically for interaction. And Delft, I should highlight, are probably the most important ones. And the other ones I will keep up for a while that are related to suppliers. We have DLR actually for our future experiments on the contour tooling that we'll do in a couple of months' time. Okay, I think this is all. I'd like to thank you for being here and for watching, for those who dialed in through internet. And I have one last slide that is actually showing a bit the time overview for today. So at 12 o'clock, onboard operations will start, actually in 5 minutes. We'll be on console for setting up our equipment on the space station. We start around 2 o'clock with software installation on the joystick in space, because of course we have used that joystick for multiple experiments already. So Thomas has developed a very nice way to actually remotely install software from the ground. So we do a software update basically for Interact as a first thing, and then, oh sorry, this is wrong. This is between 12 and 2. So at 2 o'clock protocol 1 should start, which is the stiffness discrimination, and then we got 2 runs on protocol 2 at 10 past 4 and 10 to 7. And you're of course welcome to come in and witness what is going on. I anticipate that those 3 times will be the most hectic and the most interesting ones. And we'll be switching off the live stream up to about 1 o'clock, and then we'll come online with an update.
So, good afternoon. Just to test a quick mic check. Okay. Hey guys, here this is Emil the Nexter speaking from STech Noordwijk again. Here to give you a short update of what's going on currently. So on the screens behind me, you can see that the team is in contact with astronaut Andreas Mogensen to set up our haptics joystick. They'll be probably working on this for the next hour or so, and we really would love you all to tune in at around 2 o'clock. That's the time here, so we keep the 12 o'clock GMT time for people in different places around the world. You can do your own calculation. At that point, we'll be doing our first experiment, Protocol 1 of the Interact experiment, where we'll have Andreas Mogensen use the haptic joystick to control a setup that we have here in the back, and we'll have close-ups of that later on, where he will use, we have a haptic joystick here also set up to be in synchronous with the joystick on board, so that he can probe different stiffnesses here that we present to him on Earth to see if he can feel the differences in stiffness that we supply to him. And this is really the data collection part of the experiment, where later on around 4 o'clock here, 2 o'clock GMT time, we'll have the rover be controlled by the astronaut. So those are really the two times that you need to keep in mind when you're viewing the live stream, 2 o'clock and 4 o'clock, or 12 o'clock and 2 o'clock. We'll have the live stream up and running for a little bit. We'll put the sound down because we can't really broadcast when we're directly in connection with the astronaut. But once we are able to broadcast, we'll, of course, bring it all back. So thanks a lot. Thanks for watching. And we have, just before I go, we have a small video prepared for you, which is an introduction of Protocol 1, which the astronaut actually was supplied with. So this will explain to you a little bit about the first experiment. So go ahead.
So this is the space part of the Interact Protocol 1 setup with the one-DOF and the tablet. And you see here behind the ground part of the experiment, which has the engineering model of the one-DOF and a spring simulator, a stiffness spring simulator here. So this device simulates varying stiffnesses of springs, which you can change in your stimulus. So let's log into the screen by homing on the Windows button and starting the Interact app. I'm going to use the first name of a famous astronaut here to enter. If you have a typo, you can use the backspace button or the clear and enter a 4-digit name. Now I'm going to start Protocol 1B, which is the object stiffness discrimination. You'll first get some introduction about the protocols and a sequence summary, but essentially the conduct is fairly simple. It is very similar to Protocol 6 of the Haptics 1 experiment, with the only difference that now the stiffnesses are not rendered locally on the one-DOF, but actually remotely on Earth through teleoperation. And you're receiving force feedback on the stick. So right now the first stimulus is selected, A, and I can use this handlebar to actually control the slave unit to engage with the spring, which will give me force feedback here. And after unloading from the spring, I can select stimulus B. Stimulus B is set once the actual stimulus is highlighted in green. And you can again move and probe the second stimulus. And then decide which one has been the stiffer one of the two. And press next, which will move you to the next trial. So every trial is similar, and you can cycle through the number of trials which we will set on ground. In the beginning of the experiment, it will be about 120. Important to note is, once you press into the stimulus and you apply a force, if I now intend to change to B, the system will not allow me to do that. And it will be set back to A, so always the stimulus that is highlighted in green is the actual one that is set. I need to offload the joystick and swap to B. And now I can probe the level B. And I can select whether A or B is the stiffer one and press next. After you've completed the trials of the experiments, after testing your last pair, you again move next, which will finish the experiment automatically. Up here you have motor enable, which enables if the motor control is pressed, and tail operation, which enables if the yellow start button is pressed as well. So if I do my last selection here, next we'll finish the protocol, which will move you back to the homing screen and allow you to retrieve the data via the memory stick. You see also that the increment of the trial has increased to 1, showing that one trial has been successfully completed. So this is the space part of the Interact Protocol 1 setup with the one-DOF and the tablet. And you see here behind the ground part of the experiment, which has the engineering model of the one-DOF and a spring simulator, a stiffness spring simulator here. So this device simulates varying stiffnesses of springs, which you can change in your stimulus. So let's log into the screen by homing on the Windows button and starting the Interact app.
So, test, test. This is Emil de Nexter speaking again from the Telerobotics Lab. Right now we're giving you a real behind the scenes view. So right now on the monitor next to Kevin you see a still image. Right now we have a loss of signal period actually where we have no connection or no video connection with the ISS. Once the connection is back you will see the astronaut on this screen continuing to set up the haptics 1 joystick. And anytime anytime I can comment, I will pop in every now and then to explain a little bit more about what you're seeing. Here in the foreground, the little red camera, you can already see our Protocol 1 setup. The camera is filming a haptics joystick that is in connection with another setup that we have that is going to be the virtual spring that the astronaut will be pushing up against. So this virtual spring is, we kept it virtual so that we were able to set it quite easily to different settings. And on the ISS, the astronaut will have the tablet PC with the interface on it, whereby he can switch through the different steps, different parts of the protocol, where he will receive different stiffnesses, which he compares to each other. He will have sort of an A and B test. And he will tell us whether or not he thinks the spring is stiffer or less stiff. And hopefully we will gather some really good data, really good haptics data in this experiment. This is Emil checking out for now. Enjoy the video stream, and I'll talk to you later. So here's Emil again from the Telerobotics Lab. You can't see me, but we're both watching the same thing. As you can see, the signal has returned, and we are now able to watch our astronaut continue with the setup. We have noticed that he has, Andreas have some delay in the setup, so we might not be able, might not be totally ready at 2 o'clock to start our experiment immediately. But it shouldn't be soon after 2 o'clock that we're able to start if Andreas does his best. So, over and out for now.
Hi, so we are still waiting for Andreas Mogensen to set up actually the Haptics One onboard equipment, which is a force-reflecting joystick and the tablet PC. He's slightly delayed because there's a lot of activity planned for him in a very short time. So we'll be standby, and following the setup we'll do a software update which should have taken place by now, and at 2 o'clock the experiment will be shifted, unfortunately, very likely to 16:10 when our second slot was planned, and we'll hope that he can install our experiment software before breaking to the public relations announcements.
So here's Emil the Nexter speaking again to you. As you just heard from Andre, because of the delay, we have to shift around our schedule a little bit. So Andreas, the astronaut, will continue setting up and doing a software update for the next, it seems until the next hour. So our slot of 2 o'clock will be the next experiment block. This is 2 o'clock GMT, so 4 o'clock here in ESTEC in the Netherlands. Until then, we'll continue to stream the shots of what's going on in the background. I'll try to get some people in to talk about the experiment a little bit more. What I do have are a couple of prepared videos for the astronaut that I can stream to you again. This time we'll be streaming the second protocol, which is the rover protocol. And these are the instructions that Andreas received while he was on board the space station in preparation for the second experiment. This is the experiment you'll be seeing at 4 o'clock or 2 o'clock GMT time.
So Interact Centaur has a mobile platform that is rough terrain compatible. It has 4 wheels and 4-wheel steering. So Interact can go forward, backward, and you will be able to command it in increments of 10 centimeters, 50 centimeters and 1 meter, and it can do spot turns, and you will be able to command increments of 10 degrees, 45 degrees and 90 degree segments. So the Interact Centaur has multiple camera systems which you can select from. It has the driving camera on top of the vehicle, which is located on a pan-tilt unit, actually a robot arm, that allows you to pan and tilt the camera before you drive. You have a front HazCam between the wheels and a back HazCam behind the vehicle, which allows you to see the shaded areas that you can't see through the main driving camera. On the robotic arm you have a tool camera, which actually brings a close-up view of the tool and the pack and the taskboard. Once you're near to the taskboard for the insertion, you're free to select that one. The robotic arms of the platform are 2 KUKA lightweight robots that are controlled in impedance control mode, which means they can be compliant to the environment and relay contact forces in very high fidelity to your force feedback joystick. The robot arms comply to external forces They're equipped with Cartesian force torque sensors, with a gripper, and they're holding the pack. And we instrumented the pack with a laser that actually allows you to give information on spatial depths in a monoscopic stereo view. So when you're closing in on the taskboard, by looking at the laser spot on the surface, you'll be able to confirm whether the pack is well aligned to the hole or not. The first screen gives you an overview of the task. In the second screen, you get the sequence summary for the task, which consists of first locating a taskboard. For this, you will use the camera head of the rover and pan and tilt the camera to identify the taskboard in the room. Afterwards, you will use the motion platform of the Interact Centaur to drive to the taskboard in a favorable position. You will be supported by virtual reality overlay and predictive information that compensates for the time delay between space and ground. After you have reached location of the taskboard, you will use the robot arm to manipulate a pack into a hole on a taskboard. So once you're ready, you go next, and this brings up the first screen of the actual experiment. You see here a live video feed from ground, which you can identify that it's functioning by a green dot that moves on the upper left corner of the video feed. In the video feed, you can change the camera by choosing any of the 4 camera selectors here that correspond to camera locations on the rover. So if I want to change, for instance, to the tool camera, which is located here on the right arm of the robot, I press tool, and the camera view changes to the tool camera, which is now pointing down. For this recorded video, the experiment also makes use of 850 milliseconds of time delay between this system and the robotic system, which is located in a different room here at ESTEC. So I'm going to go back to the head camera. We also have a front HazCam and a back HazCam, which you can use for driving. And you see here 2 widgets. There is the navigation widget, which is permanently shown, which shows the orientation of the rover in its world and the orientation of the camera head in its world. With the target finder widget, you can control the pan and tilt of the camera to look around the room to identify the taskboard. You see a prediction of your command here in the pan widget of the camera. And I'm needing to look around to find the taskboard. The taskboard is a small mechanical tool which consists of pegs and knobs and allows to do tasks on. You can scale your set point by pressing this enter button here, 5 degrees, 10 degrees, 30 degrees, or 1 degree. And I'll put it on 30 degrees to make faster motions by certain increments. Down here in the navigation widget, you see the camera icon predicting the future location of the camera. So there was a very big delay on the camera now, and I overshot basically to pass by the taskboard, which is located here. So I'm trying to fine align the camera now to the center of the taskboard. Once it is aligned, you can press the Place Target button, which places the location of the target in the rover coordinates frame, so you can keep spatial orientation while the camera zooms back to the driving mode. When the rover drives, the camera always looks forward. Now we are in the rover drive control panel, and what you see here is the current position of your rover indicated by a virtual square projected in front of the wheels, and in light yellow you can see the prediction of the rover command that you can issue by the rover command buttons here on the left screen size. You still have the navigation widget here, and now this widget indicates the distance of the rover to the taskboard. So the task now is to actually drive to the taskboard. by using this widget here. And again, you can change the step size arbitrarily between 0.1 meter up to half a meter and 1 meter, or 10 degrees, 45 degrees, and 90 degrees. So since the target is located to the left, we do a 90-degree turn to the left. You see on the top end of the screen the feet of the taskboard and green overlays here which indicate the position that you need to drive to. So it is the scope for driving to align those yellow marks with the green ones, which means you have to advance and turn to the left. The platform only does straight line motions and spot turns. So a good strategy is to drive at a 90-degree angle to these green markers to the point where the distance doesn't minimize any further, then do a 90-degree turn and approach the green. And it will require some fine-tuning. You see the distance minimizes, and if I keep incrementing the distance, it still minimizes, so that could be a pretty good location. Turning back left, and you'll see that you still have to increment your direction on the right hand side. Drive another meter. And a little bit less. And we'll turn left again. Should be fairly well aligned now. So let's try and approach this. Now you can see that the next button is enabled, which means you're sufficiently aligned with the green target spots. By pressing next, you go in the arm control mode, which allows you to insert the peg which is pre-inserted to the robotic arm. The tolerance from the peg to the hole is only 150 micrometers. And it is the scope to insert the peg into the top right-hand corner of those brass holes that you can see here. So the GUI first asks you to align the arm, which initiates an automatic sequence to pre-align the arm over the selected hole. Okay, I press align to pre-align the arm. And while the robot arm is aligning, the other widgets are blanked out until the motion of the robotic arm is finished. So now the alignment didn't perfectly work, so you're free to press align again, and it will make another fine alignment of the robotic arm in front of the target hole. You can see on the ground a laser dot that is projected out of the tool, how it disappears in the hole, indicating fairly well alignment. You can change to the tool cam to verify that the peg is aligned correctly with the upper right hand hole. And the task now consists of inserting the peg with a joystick to a depth of minus 40 millimeters. This widget indicates the depth of the insertion of the peg from the target, or the distance of the peg from the taskboard. Once you press the motor on the yellow button on the joystick, the motor indicator will turn green, which means you are in control in real time of the robotic system. And any significant force that is rendered on the peg will be reflected to your arm. Moving forward will lower the peg. And you can see the distance being minimized. The joystick will center you with a small force to the middle position, because you are giving a rate control input. So if you're moving off the center position, you will feel a small spring pushing you back to the center, which allows you to actually stop the motion again if you like. So let's try and do the insertion here. And you can use the toolcam to verify the alignment. While this widget is shown, you can still use it for fine manipulation of the arm. You can change the step size of linear motions here and of rotational motions here. Be careful with rotational motions. I will set the step size to 5 millimeters and move the peg slightly to the left. If the widget here is not enabled, it means you're too close to the zero position from the taskboard. To demonstrate this, I will move the peg forward and you will see the widget on the left-hand side being disabled, which is to prevent that you can execute motions while the peg is inserted partially into the taskboard. If this is the case, retract the pin by moving backwards, which should make the widget again usable. And allows you to fine-tune the pointing of the peg to the hole. If you're not seeing any laser reflection, it means you're well aligned and you can perform the insertion task. And you can change to the head camera to get a better situational overview. If you're not sufficiently well aligned, you will feel a force feedback on the joystick, which means you have to retract and fine-tune for another insertion attempt. Right now, I inserted it to minus 40 millimeters, which is the goal of the experiment. And from this moment on, the finish button is enabled, which will finish the experiment. Which concludes the run on Protocol 2 of Interact. You see that the trial number has incremented here, which means that the experiment was successful. And now you can go ahead, copy the data by pressing Copy Data button and exchanging the USB connector with the data link to a USB drive and press Save.
So we're back. Here's Emil de Nexter speaking again. We have some news about the situation. We know now that the astronaut is delayed about an hour in his proceedings. So if we're lucky, in 8 minutes' time, we might get a chance to check our connectivity with him. So we don't have enough time to complete the whole first protocol, but we will see a connection on our GUI, on our ground GUI. And from that point, we know that at least our connection is working and going. We might see some movement on our joystick. The more time we have, the more we'll see. The less time we have, it basically means we get shifted to 4 o'clock. That's all for now. In a minute, when we do have connection, Andre Sheila, the lab PI, the one you see here on the screen in the left, will be talking to the astronaut, and you guys will be able to follow along with this. Thanks for watching.
Status, but does it connect at all at the screen? It doesn't, no? We're on the wand-off.
Yeah. I mean, I'm logged in, so it's booted. That was the
Yeah.
Okay, so we're
We
fading-
verified from ground that the wand-off is booted.
Excuse me. We're fading Andre in now, so you guys can listen along.
Oh, good. It's in. It's in. It's in. It's in. Yes. Okay.
Hast du das auf dem Dingsmann?
Right, so he installed the tablet software. He seems to have just switched it off.
Understood you're sending us the PAO event, so we don't
Yeah.
have to change channels. Makes it easier for us.
And this is Munich on 3. I think we are at a good break point now. We're gonna stop here with the interact activities and get you going with your PAO preparation. Alright, I copy. So I just have 5 left and 4 sessions.
Can you open the procedure, please?
And,
He switched the tablet off. I hope not. Haptics PI for Damek on Colcord. Can you have him read back whether the wand-off is switched on? Why did he switch it off? It was still not finished, the update. Nine seconds. 90 seconds. Can he put it back on when going to the PO event so we can check status from on ground? Please ask him to switch it on. And have the memory stick switched off, so memory stick removed. What is he doing?
He has to get some space to stand for the PAO.
So we will have a better.
He's putting it in temp store, no?
No. It stays there.
Okay, it's his first time in space. He's now going for a media event, but I think the software update was done, but we couldn't verify it because he switched it off So we'll do that first thing at 4 o'clock. We'll check software status and then directly go hot. So at 4 we'll have the experiment as it looks, if we installed it properly. 90 seconds is tight.
Was ich sehen konnte, hat es nicht geschafft.
Huh?
Das Execute hat es nicht drauf.
Nicht drauf.
Also bevor es ausgestellt hat. Okay, kann sein, dass in den letzten 22 Sekunden drauf war, aber
Haben wir die 90 Sekunden abgedatet von Interact? Nee, ne? Weil im Procedure stand, dass es 90 Sekunden anlassen soll und dann ausschalten. Und das hat dann strikt nach, das war das Haptics 2 Procedure.
ja, der muss es ja nicht. Okay, ja, stimmt, steht Shutdown.
Scheiße.
Just a technical little error. Are we live? Can you hear me on audio? Okay, thanks, Eloise. It's Emile Denexter again from the Telerobotics Lab. Thank you guys so much for watching, all 400 of you. That's pretty great. Last time it was about 60 for our previous experiment, so we're really excited that there are so many people watching. Here to entertain you a little bit and to answer perhaps some questions. I'm going to grab some people from the lab and answer some questions. So behind us, you can kind of see the rover, I believe. And you can see it roving around a little bit. We're doing some pre-checks right now to get ready for 4 o'clock when we're actually going to do our first experiment, which is Protocol 2, which is the experiment where Andreas Mogensen will take the rover, drive it around, and actually do a sub-millimeter precision assembly task on our task board on the other side of the hall. We'll have close-ups of that once it actually starts. So we have about an hour to fill until it happens, and I'm going to bring Stefan Kimmer over.
Hi, Emil.
Hi, Stefan. How are you doing?
Good.
So we're gonna. The first question is, what sort of video feed is the video feed that the astronaut receives most likely?
It's a custom software, but we're using a commercial codec. So it's
What's the codec?
a H264.
Okay, so it's a very no.
But we actually have custom transport protocols.
Okay. Do we have so many other questions? Oh, we have a question for Joao. Joao Rebello, a good friend and good colleague of mine who is not happy to be on camera, perhaps, but we're going to grab him over here for a second. Joao, have you gotten the question or? Okay, so the question is, how do you solve the signal delay problem? So as we've explained before, we have about a second signal delay that the astronaut receives when he's controlling the robot. How do we solve this?
So that's correct. So the way to solve this or to address this is to do it using a technique called model mediation. So this means that we are in fact creating a sort of local model of the environment and then transmitting this over the delay channel. And this prevents the delay to cause stability problems on the force feedback.
So if we have instability, can you give an example of what might happen?
So what could happen, for example, is that vibrations will be appearing in the system. So if, let's say, the robot arm is touching the environment, you will basically see the robot arm wobbling very heavily until it can eventually cause damage on the environment. So this would be the kind of problem that would happen.
Okay, thanks for answering. So here we have another question about the video codec for Stefan. Do you remember the question or from her?
Yeah, I do.
Okay.
So we done 265 is because it was originally designed actually for movies, and at the time we developed the software, it was also not yet available. So it is not yet ready for our transport protocols.
Okay, so it's just a matter of catching up. Do you think this will happen eventually?
That will definitely happen, yeah.
Yeah, so I mean, as we go along, of course, computers and the software updates at such a rapid rate that it's usually hard to keep up. Once you have a stable system, there's a new thing that comes out. That's with every part of our thing. Currently, in our robot, to control the whole thing, we have about 8 small computers running to control different parts of it: the head, the arm, the 2 arms, the grippers on the arms, the camera vision, etc. And well, the computers that are in there now, by now they're already outdated. So we could easily update it again. But if we do this, we continually run into basically having an unstable system or having to redo everything. So, but it is really great. I mean, the longer you wait to do your experiment, the better your system is going to be. It really does make a difference nowadays.
And Emil, I must say, for space, hard and software, we are still very top-notch, because space usually is fairly conservative, so we are really very fast developing in this domain.
Yeah, as Stefan says, you know, we try to go really as fast as we can. The whole rover, as you might have heard, was, you know, conceived and built in a year and a half about. So, you know, in that time frame, you look at the different components that you have and you put them together in such a way that you create a balanced and stable system. And well, hopefully we'll be able to use it for quite a few experiments, and well, we're at a point right now with technology that we're able to do so much with such little devices. All the devices, all the computers that I were talking about inside the robot, of course, are miniaturized. So they fit in your hand. They're different brands, which I'm not going to mention, but very highly powered, high power density, I guess you could say, for the whole thing. And that goes for everything. So we have some more questions that my good friend Jan Smisek is going to answer. You might have been told the question. I don't know the question.
I do know the questions.
Question: is there force feedback in general, or? Okay, so Jan is going to answer a question. Maybe you want to repeat the question.
I will repeat the question. Thank you. So the question was if there's some kind of a preview on the force feedback. So basically, we are operating over 800 milliseconds of time delay. So the astronaut actually moves the joystick and then would have to wait almost a second to start feeling the force. Well, it might be awkward for the astronaut. It will be also difficult for the controller. So what we are doing is that once he touches the environment, we are estimating a model, meaning we estimate the position of the environment of the spring and the stiffness of the spring. So next time he's going to approach it, he will feel basically at a precise location. He will feel a contact right away. He will feel the stiffness of the spring, and it should feel natural to him. So to which extent he can use it, we'll have to find out. But
no, I'm going to continue on this question a little bit. So you've explained we're using a model-based system to deal with the delay right now.
The proper term is model-mediated.
So a model-mediated system, and this is for, as I understand it, for delays that are a little bit longer than you would normally have. Why? Could you maybe explain or distinguish between, because we use a different system when we're dealing with very, very short delays. Can you maybe talk a little bit about the difference between the two?
Okay, this is very correct. So we have two problems. One is for the system, let's say. So if you are, I will look to the viewers. Thanks. If you are dealing with short time delays, meaning maybe less than 100 milliseconds, then the main issue, the main challenge is actually to keep the system stable. So then we are basically just trying to monitor the system, to add some extra damping to make sure that the machine, due to the delay in the feedback, is not going unstable and crazy. But we do, when we have a feedback or delay around 1 second, then we have to also make it easier for the operator, for the astronaut in this situation. So then we provide the preview, and we try to make it, let's say, more robust and more easy even for him to operate. So that basically brings the two differences.
Thanks for answering the question. We have another question. So the question is, will this test work if the distance for the signal to travel, or the distance between the user? So, space to ground, 400 kilometers away.
Right. So the actual distance of 400 kilometers, that accounts only for maybe 10 milliseconds of the time delay. And the 800, or the remaining 800, these are coming basically from the distance we have to travel up to the geostationary orbit, to relay satellites, then to the US, and over the ground here to Europe. Yeah, so it will work, and it can work over longer distances.
How many Raspberry Pis in the robot? Not so far, but I like the comparison. So what we here at the Space Agency have, or what we're able to use as materials to build rovers like these, are, in a sense, very similar devices. Like I said, we have about 8 computers in the rover right now, and they are fanless computers. So like the Raspberry Pi, it's a very small, power-dense computer running our different systems. So it's not a strange question to get that. I'm sure there's no Raspberry Pis in our rover, just to make that clear. Although it wouldn't be a crazy idea to make a miniature version, perhaps, of the rover using Raspberry Pis. That's not crazy at all. Okay, so we're going to answer maybe some more questions, or I'm going to talk a little bit about the delay and what it's caused by. As Jan just explained, the signal has a long travel distance, and earlier Andre explained in his experiment or in his presentation that the signal actually travels through this route. It actually goes from the space station to the TDRS NASA satellite relay system. So this is a geosynchronous satellite system that, just to explain a little bit what that geosynchronous part means, it goes basically at the same, it goes in synchronous with the Earth. And that is to make sure that the time that we actually have signal is more or less constant. As when we communicate with the space station, we have to deal with time frames. So there are points at which the space station is going to be in a position around the Earth where we're not able to communicate with it. To solve this, there are the different relay systems in place right now so that we have longer time frames. If we didn't have that and we would wait until the space station would fly over, we would have about a window of 7 minutes to do our experiment in, and then we would have to wait perhaps another couple of hours before the space station returns again, and we have another 7 minutes. Right now, we have about 90 minutes to do our experiment, and we have only very, very short loss of signal time. And from these, just to make the path of the signal complete, it goes from from the ISS to the geosynchronous satellite system, down to ground in the U.S. to several different stations in the U.S., travels overseas to Europe, and it actually has to Europe in Germany, and then it goes to here, the Netherlands, at ESTEC, at our system here, and it goes back again. We have actually a round-trip delay of only nearly a second, and that's actually quite short in our opinion. We've had to deal with longer delays than that. So we're gonna answer some more questions. Do you guys have another question for me? Did we prototype in Kerbal Space Program? Have you played? That's not my question. That's not your question. Has anybody here played? Sure. Kerbal Space Program is awesome. I should try it sometime. I don't have Steam installed. So we have another question for Eloise here. And she knows the question. Are you going to repeat the question?
I will repeat the question. So the question is, what sort of skills do you need to join this lab? And it comes from an electrical engineering student. And I just wanted to say that most of us in the lab have backgrounds of engineering. Maybe it's control, maybe it's electrical, mechanical. Personally, I did mechatronics engineering. And I would say that the team is really multidisciplinary. But of course, you need to have good programming skills. We use in the lab Linux, and we program in MATLAB, Simulink, C++, C, Java. Trying to think of other things that we use. Bash, yeah. So definitely some strong programming skills, but also a good overview of electrical and hardware systems, and just it's typical, but a big sense of enthusiasm for these sorts of projects because it takes a lot of time and a lot of dedication.
Thanks very much, Eloise. And so there are questions. We have another technical question coming up. How many degrees of freedom in the robot arm and the joystick, and perhaps the difference between the two? So, should I have you answer this? Would you like to answer it? So let's start with the joystick. How many degrees of freedom?
So the joystick itself is just 1 degree of freedom, and we use this degree of freedom to move the peg in the robot arm in and out. So in that 1 degree of freedom, you have force feedback. But we also control 4 other degrees of freedom via the GUI. So for that, it's up, down, left, and right, and rotation up and down, and rotation left and right. And that's also to manipulate the peg to get it into a good alignment with the hole. The robot itself, the rover, can go straight. Okay, so the rover has lots of different operating modes, but we only use 2. And this is basically 4-wheel drive, forward and backwards, and turn-in-place mode. There is also an option called crab mode, which is where the robot can almost steer sideways, but we haven't put it in for the astronaut simply to simplify the maneuvers he can do. And as you can see, we're in quite a constrained space, but it's a useful feature of the robot.
Okay, it's more or less, I think, so let's talk about the robot arms, the degrees of freedom that the robot arm has.
So the robot arms, which are Kuka manipulators, are really, really cool. Technically, they have 7 degrees of freedom, which is the same actually as your human arm. So they're designed to really emulate what a human can do with their arm, including the shoulder. So basically, in your human arm, you have 3 degrees of freedom in your shoulder, 3 degrees of freedom in your wrist, and 1 degree of freedom in your elbow, which means that you can reach, say, this space in this orientation, but you can also reach, okay, I can't do it now, but you can also reach the same orientation with your hands in 2 different movements, 2 different orientations. And this means that you can avoid obstacles really easily. So our robot manipulators also have 7 degrees of freedom.
So I'm going to elaborate a little bit on that because as I maybe spiked the question a little bit, I said there's a difference, of course, between a 1 degree of freedom controller and a 7 degree of freedom arm. Of course, in the future, we hope to add these degrees of freedom to our control system. Anybody who has seen our website knows that we are also working on exoskeletons to use the controller. So in a sense, those exoskeletons are have pretty similar technology as our controller right now, or as our one DOF setup right now, but it'll have multiple degrees of freedom. So it'll basically have one of these joysticks for every joint of the arm. And with that, you'll have, a much more intuitive way of controlling these robot arms, because you'll pretty much see the robot mimic your movement, and you'll have the same functionality as our 1 degree of freedom joystick, that in the sense that it'll have haptic feedback. So you'll feel haptic feedback in every joint of the arm. So that basically lays out a little bit of the future and why we're doing this experiment right now. We only have the 1DOF joystick paving the way to experiments such as these. The 1DOF experiments also allow us to capture a lot of data from the astronaut to see how his sense of touch is when he's been exposed to microgravity for quite a long time. Sorry, I was just focusing. Okay, we're gonna. Okay, we're gonna talk about the applications on Earth. Sorry that I lost my train of thought there. So the applications on Earth. Well, when controlling robots over long distances, you can understand that this maybe applies to situations or any situation where you'd rather send a human. Rather send a robot than a human. So think of situations that are dangerous to humans. Well, we like to give the example. Situations such as the Fukushima disaster. Here, you'd rather send a robot than a human into the disaster zone and control that from a long distance so that you're basically safe. Other situations in space that that we can talk about, because we're the space station here. Think of there's been a lot of talks about going to Mars. Well, if you know about the missions and going to Mars, there's not going to be much there when the astronauts arrive. And if you've ever seen an astronaut come back from space, you'll know that they're pretty darn sick. They have a hard time using their muscles, and they really need to recover for a couple of months. So instead of going down directly onto the surface of Mars, we could first send several robots and control those from, say, a space station that is orbiting around Mars to set up base camp before the astronauts land, so that they have they have a habitat to recover in once they do land. So we have some more questions. I'm going to bring in Frank van der Hulst now, my mechanical engineer colleague. A suit-like operator. Will there be a more advanced interface? Well, I briefly spoke about the exoskeleton. Maybe Frank, you would like to elaborate a little bit on that. I've explained to them, to the viewers, that our haptic experiment can be seen as, per se, a single joint in what could be a multiple joint system. Could you talk about this bit?
Okay. Yes, of course. Thanks a lot. So the question is, if we're expecting suits, basically exoskeleton suits in the near future, I would say it would be possible to build suits if we combine like all the techniques that we have at this moment. We could combine our own exoskeleton arms, maybe with our Grassmasters, which are exoskeletons for the hand, in fact. Also, a lot of universities are doing studies in exoskeletons for legs, basically. They could be used for rehabilitations or for force enhancement. You could combine those systems. However, we should think if it's useful to have a suit like this. Where would you use it for? For like full body rehabilitation, that could be an option. Full body control could be possible. However, I would suggest to focus first on separate systems.
Yeah, so for a full body system, it might not even be practical in our situation. But a single or double arm exoskeleton is probably something that our lab will work on. So we have an update for? Okay, we're now going to get an operational update from Andre. Andre Sheila, our lab PI. I'm not going to use his nickname. Andre Sheila, our PI, give us an update.
Right, Emil, thanks. Well, okay, a small update on what we have done so far. We actually managed to set up our onboard equipment, our haptic joystick. We booted our haptic joystick and the tablet PC, and we left off actually installing the software for our new Interact experiment. So it's still installing at this point in time, and we are logged into our computer right now to see the status, and it seems that some progress has been made, but not the complete progress yet. So we are still recovering the situation. There was a little bit of delay because the setup took longer than expected. There was a lot of equipment and a lot of activities actually planned for Andreas, who has been in space for the first time. While doing his conduct, he was wearing another experiment, so it's a very difficult situation also for him. But he's doing really great. He has set up our equipment wonderfully, and now we're looking forward to getting back online with him at 4 o'clock. We'll be debugging some of the software configurations at 4, and then we'll be directly enabled space to ground with Andreas to talk with him and to start into Protocol 2, which is our rover experiment that we'll do over there with the Interact Centaur.
So we can continue with questions if there are any, and we've seen quite a couple of questions, or a question pops up quite a lot, is about the rover's wheels, and I'm going to bring Doa Emerdag, a new student in the lab, also an industrial design student, who's going to explain why do we have rubber tires on our rover?
Hello. So it's actually very easy topic. The rover is actually designed for testing on Earth. So what we are testing is the technology that will one day be used in space, but the place we are testing is still on Earth. Actually, like exact place is actually some sand dunes that might give us a better idea how the technology will behave in a space application. So the rover, you will see a lot of design considerations on the rover that makes it function better when it's operating on, say, sand dunes. It's a weatherproof, which is still being worked on. It doesn't let dust in easily. It its ventilation system has filters in it, and if it gets caught under rain, it can survive rain, which is very important in Netherlands. So that's why the rover has wheels, so it can operate on Earth.
Thanks for answering the question. Yeah, operating in rain. It's currently in a setting right now, not quite weatherproof, but Doa is working on some weatherproof systems during his graduation, which will solve this problem. The original plan actually for today was to have the rover rove outside, but the past couple of days have been pretty bad weather, so we're quite happy that we actually chose an indoor setting to do our experiment in. Let me just see if there are any more questions coming from you viewers. Otherwise, I might have to turn off the volume again. Okay, my colleague here wants to say something.
It would of course be really nice to have the rover operating outside under rain, but now I'm looking around that only the robot would be happy about this, and the rest of the people, I don't know how we would keep everyone else happy. So yeah.
Maybe party tents next time, or yes. Let's. We got the request that you guys want to see our monitors. So, Case, let's see where we have a camera guy who's set up to move the camera around. I think this is his camera. Okay, so guys, I'm gonna get the camera and we're gonna show you a bit of the screens. Could someone take over?
I can take over. Emil? You don't need to press anything. Okay. So Emil will take the camera. I will talk through each of the screens and. Okay, maybe you could start here to the left, Emil. You start with our GUI. So Emil is now moving the camera and setting it up so that you can see the screens. So here on the big screen you can see the graphical interface that the Astronaut will use, but the version you see on the big screen is actually the ground version. So we get a copy of what the Astronaut sees in space in order to be easy, to make it easy for us to actually follow the experiment. Otherwise it's very complicated with the time delay and the communication delay to actually know what's happening. So that's what's on the big screen, and on the tablet joystick combination, then you see actually the setup the Astronaut will use on the space station. So that's an exact replica with the tablet and the joystick, and that's the real graphical user interface that the Astronaut has access to. He can then select the different protocols, and if we move then farther to the right here, according to my position, then on the big screen there you get the video feed from the ISS, and the screens in front, they are basically the operations screens for the ISS. So that's everything that's related with operations. I will. You want to go talk to Kevin? So I'll let Emil talk to Kevin.
Okay, I want to talk to. I don't think we have a lot of cable, but Kevin, can you leave that place or? Okay, so we don't have a very long mic cable, and so could you tell us a little bit about what you're looking at?
Yeah, sure. What we have here is our ops console. So basically, we have the live KU downlink from the station which we've watched earlier, which is coming from one of the 6 KU downlink stations. What we're looking at here is the voice key sets, which are used for communications to the crew on board or to all the other stations at the control centers. In Oberpfaffenhofen is the Columbus Control Center down south from Munich. Some of our other tools we're using are console logging, and just let me switch a page here.
Let's have a look at the other page.
And this is called the Optimus Timeline Viewer. So every activity that a crew's doing on board, you can see by the timelines here, are quite scheduled, how you say, for fitting an astronaut's day every 15 minutes or 30 minutes, how long the activities are. One last active component we're looking at on the, how you say, the Mission Control Center pages would be our procedure viewer. And basically this is what the crew's been trained on to do the experiments. So if you, I don't know how well you can see this on the screen, but each of the experiments also have a detailed breakdown of the actual procedure. And for the Interact, we have over 27 pages of procedures that are all electronic. We have a hard copy as well, because in case Mr. Murphy decides to visit us, we still have a hard copy. And the crew on board also is using the same procedures, and that allows all the experts here to walk through with them as well, real time.
So is he actually using that paper when doing it himself, or is he being talked through it?
On board they have what's called the space station computers, SSCs, and they have exactly the same layout as here. So he's going through the procedures, looking at the picture step by step by step. If he has problems with 2.4, he can voice down, and that's where our PI, Dr. Sheila here, someone would say, okay, at this, please swipe over, and it allows for some real-time interactions. But all the procedures on board are generally run through verification. I also go through experiment sequence tests to make sure every step is exactly what has to be done.
Maybe I can ask one more question about the last screen, or maybe not. It's the widget screen, and it looks probably the coolest of all of them because it's dark.
Yeah. No.
Can you tell us about that one?
Yeah, absolutely. So what we have, I'm just going to look over this way so I see. What we have is on board a lot of data you can imagine from the various telemetry systems and so on and so forth. So basically, the big white one is something called caution and warning, and that allows the ground control teams and the flight controllers in Houston, Huntsville, or COLCC, Russia, to see what's happening on board with respect to alerts and such. The one that you see there that says go, with 4 little boxes, that gives us our indication when we have AOS, which is acquisition of signal, and LOS, loss of signal. As the station does an orbit every 90 minutes, as we explained earlier, it uses a combination of TDRS from NASA, the satellite system, to relay the data down to White Sands, which gets distributed to Houston for the systems control, and Huntsville for payload, which we get our data via that mechanism. And some of the other screens you see there are all about Columbus environment and our comms.
Well, sounds like someone's on the system, and you might be called. Thank you very much, Kevin. So, let's switch to the other camera now. For now, the rest of the screens are off and not important right now. Maybe later on in the experiment, we'll get to see a little bit more of that. Mostly, it's software running. It's going to be a lot of computers that are ours running in the background. A lot of command line. To make sure all the systems are up and running optimally, and also so that we can actually intervene if something goes wrong. So if there aren't any more questions for now, I think we'll put the microphone down for a little bit, and it should be okay. So it's nearly 3:45. So at 4 o'clock, 10 past 4. We're scheduled to continue with our first experiment. Hopefully by then, astronaut Andreas Mogensen will be will have completed the setup. We do need to check if our latest software has been successfully installed. We'll do some debugging, and hopefully we'll see the rover rove pretty soon after that. Thanks very much, guys, and we'll talk to you. And thanks for your questions, guys.
So fuzzy, and then it's. That's the worst case you want, is like the handy going up the station. Come on,
What takes
GC.
them so long?
Because he said it takes 2 seconds.
So, protocol 2
Can't be.
or what?
I'm still not enabled on space to ground.
Yeah, but I can tell him if you want to him to start.
Yes, but I want to verify that he knows what he needs to do, because nobody could confirm he has watched the training videos.
Okay. So we'll tell him that we are still doing the enabling.
That's Pedro, he flew.
Yes.
Good message, okay.
Okay, so we'll be seeing here, basically once he's live, what is going on. That's a reduced version of what he is seeing, in fact.
Come on, GC. The loop came right off. It used to be here. There it is.
Okay, there you go.
Call flight, GC. Go. Yeah, I had to restart my interface, and I'm doing my final check now. He should see TLM on his space to ground 3. Can you confirm?
Confirm.
I confirm.
Okay, does that mean we are all good? We're all good. Okay, so haptics PI, you can go and initiate the call.
I'll do that. Thank you. Andreas, haptics PI on space to ground 3, calling from STEC.
Hello, Andre. This is Andy on board ISS. I'm ready for, I think, protocol 2, is it?
Hi, Andy. Yes, indeed. How are you doing up there?
Good, I'm doing great. How are you?
I'm great, thanks. We actually changed plans slightly, so we'll start with protocol 2 and then later on try to catch up some time to run protocol 1. So if you're ready to go, you can choose a username and log into the Interact experiment.
All right, so I already logged in and created a user, and I've got the screen with the protocols now. The choice between protocol 1A, 1B, and 2.
Right, and we'll be starting protocol 2. Did you get any chance to see our videos we had prepared for you?
No, that's negative.
All right, so no problem. In protocol 2, you'll be driving the Centaur directly, and your task will be to actually connect a connector into the task board. So the first thing you'll be seeing is the screen that allows you to get the video feed from ground.
He's fighting with his comm unit.
Right. Yeah, he had forgotten to set that up.
It's the handrail from the first part.
He's still wearing the skin suit.
He loosened it to finish your activities because it was too tight. He said he couldn't move, that's why he lost so much time.
All right. Oh, I see.
It's really quite restrictive.
Okay. So he's still wearing skin suit, but he loosened it up in order to save time. He didn't take it out entirely, but you can see that he had some difficulties moving around in that suit. So he's making his life a bit more easy.
PI, call flight, call 1 loop.
Go ahead, call flight.
Yeah, just for you, please give us a heads up when your discussion with Andy or per the protocol there is a change of config, like you activate or deactivate the subsystem or change in a significant way the Columbus configuration, just for our awareness.
Okay, I will do. It seems he connected to our protocol, so he's about to start. I'll change back to space to ground 3.
Understand.
So Andy, no reply required. We placed the task board for you somewhere in the area that you'll have to find.
Okay, copy that. So,
He's got to push the button. Just wait.
Oh, okay.
He's just going to try to drive.
Yeah, he's moving the head. Okay, he's moving the head. Perfect.
It's good.
Now he thinks he's on the moon. I hope he doesn't drive into the moon banner.
You got your override to make him feel like he's doing well.
And you can pan and tilt the cameras to look around.
Make sure you let go right off the... Doesn't seem to be reacting for him. Not really moving for him.
are there limits on the tilt and pan?
You need to click the blue buttons once and wait until it re-enables. Every time you click it, it increases one increment. And you can select the increments in the center. Okay, so he wasn't trained, so he's doing this really for the very first time. He has never controlled this robot before. Okay, he's looking at the moon panorama.
Yeah, okay, I still need the SDM lead flight to give me official directions, but just to get prepared, if we skip the microbial swab this afternoon, or if we skip it completely, I'd like to understand what we still need to do this afternoon. We have that height measurement and questionnaire, and after that, I guess you should doff the suit and put it somewhere particular, so I'd like to have a good plan for the case where we do skip the microbial swab.
I should tell you that you have some audience, Andy.
Mr. Beam call we can move to call 1.
East Beam on Coker 1.
Okay.
So he will have to do the height measurements, DOS.
Can you put me off on the other loops on the call flight?
Yes, I just have to listen in case they call you. That's all.
Andy, so the task board is covered in MLI.
So once I've found the passport, how do I drive the rover?
Oh, once you found the task board, you need to align the crosshair with it and press place target, which will move you to the next step once you find a good alignment. And you can fine-tune with smaller increments if necessary by pressing the number in the middle. That looks pretty good. Right.
Haptics PI call flight. Mine the short handover in a minute and a half.
The what?
There's a short handover in a minute.
Okay.
Copy.
So you're right now in driving...
Wait.
No, don't put
go.
it. You're right now in driving position once the camera is back, and the target actually indicates the direction you need to drive. It's tracking the target in the widget in the bottom of the screen.
There's a T-Dress handover.
When I get to drive, I use the arrows, is that right?
You use the arrows for forward and backward is up and down, and left and right is spot turns.
So if you estimate we're going to run long or...
and half of meter is the distance, so what's 45 degrees?
Right, half a meter is the distance, 45 degrees is the amount of rotation on the spot turn, and when you press these numbers, you can scale them.
For the KU handover, so this activity will have a natural end, and the other activity in the KU, but I think that...
I'm sorry, 45 degrees is what? The number of...
Turn, it's the turning degrees, so of your spot turns. If you press 45, you can change it to 90 and to less than that by 10.
Okay, copy.
Wow. This is crazy, he has never driven that rover before. Oh! Let me... Andy, no feedback required. You see some virtual overlay in the video stream. So in yellow, you see the actual position of the robot. In white, you're seeing your actual command before the time delay to the robot. And in green is the target pose where you need to drive to align the robot with. Okay, now we are space to ground. So we are out of signal for a short signal handover.
We have LOS for
LOS,
1 minute.
1 minute. So this shows that our experiment software is robust to signal dropout. So the satellite constellation is now such that none of the satellites can see ISS and ground at the same time. So it moved out of signal, and he's seeing now the screen. Once the signal is back, he just clicks resume and he can continue the experiment. That's very important because it's unplannable to do operations actually within signal periods, because as these are human experiments, they can shift forward and backward, so it's very necessary to be robust to this. Everything on? Everything good? Robot arm on?
Everything ready.
Laser on, I see.
Used to be me here.
Okay. When does ND actually
Is there also an experiment?
in the plan?
We're not even into the protocol yet, so it's a bonus.
Oh, we
Part
have time.
of the microbial swap activity.
We'll
So
start
as
the
he
activity
docks
in like
suit, he would be
1 minute.
swapping both his body and the skin suit. However, if we're just going to doff, there's no specific step to call out. He would just be doffing it, and it takes about 5 minutes. He would test to it for air drying.
Emil? Are you using this camera?
Okay, so basically if we go with that plan, keeping the microbial swab, he just needs to run the skin suit
AOS.
questionnaire activity.
Okay, there we go.
The plan, and then we only get that done afterwards doff the skin suit and tends to
Okay, so the video feed here is delayed. Don't be disturbed by it. The voice is earlier than the video, about 3-4 seconds.
A reminder for
He's
the
gonna call you now.
Davis
Yeah.
questionnaire sometime in this evening, and we can move the skin suit measurement and doffing questionnaire as late as 16:25.
Thanks.
You're hot.
Yeah, thank you. All right.
Oh, he's driving pretty good. He's doing better than you did, John.
So right now we are entirely out of control of that robot. It's purely in his hands. The only thing we have is a big red end stop in case he drives against the wall. We would even allow him to drive against the taskboard. Hey Andy, great to see. You're doing very fine. You'll have to line up with the green square that comes in view close to the taskboard.
That's the boy.
And no feedback required. In the training video, we had a little trick. Once you sufficiently line up and you have a lateral displacement, you can also do 90-degree turns and watch the distance mark on the left-hand side of your video feed. That's hard to explain over the link. looks pretty good. Can you read the alignment? He's being very cautious.
Chemical flight. Go ahead. It's just for curiosity, I thought this protocol 2 was about using the joystick and applying some force and getting some force feedback from ground. Looks like a different thing we are doing, but that's all as we expected. Yes, protocol 2 is running the Interact tower on STEC, so they are driving around with the rover down there, and he will do that for 2 times 60 minutes. That's the plan, but they can shorten it if it's fast, I guess. I'm not sure if they just gonna readjust the rover and then drive on to get some experience. But the protocol 1B, I think it's more the force feedback, stiffness, discrimination task, so they will probably try to fit them in the schedule
Ich glaube nicht, dass er die Overlays hat.
Okay, in the big picture, what I read, I think 1B was about just more like a comms test, but force feedback from protocol 2. But okay, if that's been updated, that's fine, as long as you're happy with the results.
Otherwise, you'd have no idea where he's going.
Which is a different experiment using the same hardware. And Eurocom, is there a way that we can download or see a video of what's happening at this?
Yes.
Yeah, well, they're streaming it on YouTube with a 1-minute delay. But if you go to YouTube and watch or search for ESA Robotics, it should pop up. Okay. Okay, then Tamek call flight. Okay, let's say we go till the end of this window for Interact. Then we have this PL symbolic on the plan. Then Andy will do a few minutes of skin suit activities. When we're done with that, how do we proceed with you? It's just going to be about starting another protocol. I think they will put the kit tower back in another position and see if he can reach the task board. That is a plan for the second protocol 2 activity. But I think when this activity...
On the Andre on Space to Ground, no feedback required. There is a next button that you can only press once you're sufficiently well aligned. If you could read back whether you can see the virtual overlays. I think they're there. Yeah.
Well, definitely.
Yeah. Yeah. That looks pretty good.
Consider I've never seen the training video.
No. Oh, that's too much. So what we can't see here on ground is that he has some virtual overlay that he's trying to align, which is an ideal footprint where the rover should be parked, such that the arm can reach the task actually. So it's quite difficult because it has, wow, okay, he's next, so he can continue. That's great. So he parked excellent. Whoa, okay, don't press any and stop. Okay. He needs to turn back. He was good there. That's it. Okay. Wow. And Andy, you can also command smaller step sequences if you like to.
Hint, hint.
Am I still enabled space to ground? Yes, huh?
But he's concentrating quite.
Yeah, yeah, yeah.
I see him smiling.
So if you monitor the next button,
The smallest degree is 10, right?
affirmative. Oh, that looks right on the spot. Okay, he's in tool control. So now the camera repositions so that you can do in arm control. The camera repositions, and now your task is actually to operate the robot manipulator, the right arm. So there's a button to pre-align, which you need to press first, which brings it in the preferred position. Okay, he's aligning the robot arm. Right. Yes. Hmm? Which switch? Yeah. You can also change the camera views, Andy, by pressing tool, front and back. So tool will give you the live camera feed from the robotic hand. Yes. And the tool actually projects a laser on the task board, which tells you basically about the alignment status of the pin to the hole. So when the laser disappears in the hole, you will stop seeing it, which means you're good in alignment, probably. So now he's within, let's say, 2 to 3 centimeters.
There's arrows up, down, left, and right, but there's two types of arrows. What is the difference between the arrows?
The inner arrows are position commands along the coordinate axis, and the outer arrows are rotational commands. So I'd be careful with the rotational ones and use the inner ones for the linear motions. And you can again change the step size if you press the numbers. How with LOS?
Long time.
All right, copy
Okay.
that.
And from now on, basically, the joystick will be a rate controller to the Z-axis of the robot to insert it.
45 minutes.
Okay, that should be sufficient. Ja. 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 Wo, gib mir mal mein Handy, wo ist denn das? Danke. And you can press align multiple times, Andy. Yes, he found it by himself.
Careful with your handy by the headset, it'll go to the up to the grip.
Oh, that's my luxury photo for today.
Andre, hand it.
So here on the screen for the camera teams, you can see actually what the astronaut sees. So he's getting close in on the hole.
Is he moving anything?
Yeah, he moves it.
Oh, there, okay.
He moves it there.
Very small.
That looks pretty good.
Insert.
On the left hand of the video feed.
There he goes.
What was that?
Walked over him, man.
What happens now if I press the button that's called align arm?
Align arm will always fine align the pin towards the hole, but once you're sufficiently close, you don't necessarily need that, and you can use the joystick for forward and backward movement of the arm. If you're not well aligned, the joystick will give you a pretty tough force feedback. On the joystick, the yellow button you have to press slightly, because if you press it through, it will again disable. That's a safety feature on that yellow button on the joystick. So whenever the lamp goes on, he has completed the task. There's a small lamp left to the pin. So it's actually a connector that establishes an electrical contact once the pin is sufficiently deep in.
I have to remove this metal safety stuff, right?
That's affirmative. Just to check in.
Last
Okay, there we go. Thomas, kannst du noch mal ein paar coole Fotos von da hinten machen? Nimm meins wieder. Shall I tell him that it's 150 micrometers, the tolerance? So since we are not seeing the laser spot, it's actually rather well aligned, but I can see from here that he still needs to align it better, probably.
So he can change his camera angle.
Okay. Yeah. He's changing the camera feed. And you can watch the yellow symbol on the right. As you move forward, it will close in on the target. It's a symbol for the peg you're holding in yellow on the scale on the left, on the vertical scale next to the video. So you
Moving when I move the joystick.
For the joystick, you have to press the orange button sufficiently that the motor button on the top of the screen lights up green, and from then you're in control of the robot. But first you have to comply with your hand if the joystick gives you any force. I don't know, he's not pressing the button.
On the tablet or on the...
On the joystick.
So he's going to ask you in a second.
Wait.
That, the green virtual button that says lights up never becomes green.
Is that also if you press the deadman switch on the joystick? Right, you don't have to press it all the way in. It has 3 states. When you don't press it, it's off. When you press it, it's on. And when you press it too much, it's off again.
Good to know.
Manuel, is this model, is the model running? Can you check whether the model is running actually on the joystick?
It only lights up when I press it all the way in. I mean, when I press it only halfway, then it doesn't light up.
Okay, that's fine. Just press it as much as it is needed for it to light up, and then you're in control.
Imagine trying to voice all this up through the Eurocom.
Don't forget that.
Well, the Eurocom's paid room today.
I don't know, I don't see it lighting up here. Did the model maybe not start? Yeah. Yeah, but teleoperation is lit.
The motor doesn't turn on in this GUI, and the connection only appears if the model is running. So it is running.
So teleoperation means he's aligned?
No, teleoperation.
It used to be when he was aligned.
Yes.
Okay, he's moving it.
That
He's moving
seems
it.
to be happening when I
All
move
right.
the...
It's moving. We can see it moving. Yeah. So once you enable the joystick, it actually pushes you in a reference position, and from then on you can control it because it's a rate controller. You first comply, and then when there's no force, you can move it. It will give you a slight push to the center position first. And from there on, if you keep pressing, you can forward or backward control the arm. Okay, so he has moved it. Seems to have a slight little glitch here in the ground GUI that this motor thing doesn't light up green, but he actually was in control, so the link was there, and he can control it.
also in gray on his interface?
On his interface, it's green.
Oh, okay.
Yeah, okay, he's fine aligning it. He's very careful there to not hit the taskboard in a wrong way, which is good. So we'll leave him be careful and tell him later that he can be more daring. Okay, there he goes, forward and forward. He's inside the hole at -5, -10, -20.
He's getting excited.
Not yet. I don't know what's happening. How is LOS, Kev? We good? He got the force feedback. Okay, so he didn't align sufficiently well, so he actually now gets the force feedback, which prevents him to go deeper into the hole.
26 minutes.
Andy, I think you got the force feedback on the joystick, which is a sign that you haven't been sufficiently well aligned. So you can, by moving it backwards, extract the pin again. Yes. No? There seems to be a lot of signal delay, actually. See him closing on? Yeah. So if we get it on the video 3 seconds late and we see it afterwards here, we're having a lot of delay. We should check the MPCC status. Yeah, but this is delayed from. Yeah, okay. No? Yeah.
Hey, Data, Kevin here. I was thinking, what do you think for data coming through right now? Just for any rates you can see or such.
Okay, so he's closing in another time. And he's inside the hole at -20.
Okay.
-24.
No, because it's we're really seeing a lot of latency here, unexpected. Because from what we're seeing, what he's doing on from the space to ground video, it's like actually happening on the return video. So you guys, so you. No, I understand. But what did you say is the other? Okay, 300 kilobits up, and you said about 40 down. 40 down. Is that what you're expecting? Yeah, they're shaking their heads. That's okay. Yes, sir. No, we'll just leave it for now. That's adequate for this protocol. And no, it's just interesting that he's, let's say, you can see what he's saying coming back on the video.
See?
It's still frustrating. We just want to check everything's okay.
It's difficult, huh?
No, I know
But he's looking now at the front
we
test cam.
We also have here on the GUI that he's seeing. So I'm seeing what he's seeing. That what, you know what I'm saying? We get the video from the rover back to here.
Andy, this is Andre on Space to Ground. Either this is your. So did you receive some force feedback on the joystick? So it did not stop you pushing in, or it did stop you pushing in? Okay, let us check this. So do you read, can you read back the status on the motor indicator when you try to move it back?
You can see his GUI moving.
All right, and does the joystick give you a force? Can you feel a force on the joystick? Or you're moving back right now? Yes. Right, there seems to be a lot of signal delay. We had some news before the weekend on the KU forward link.
Stop, there's no problems there. Everything's nominal. It's best he not know that.
Once you move it out of the whole area, you can also try to align it from scratch. But if you don't feel a resistance, you can just move it in all the way. You don't have to be too gentle. Hmm?
Okay, copy that.
Yeah. The pin on the gripper?
The peg.
No. The peg on the gripper? No. Yeah. So the best thing is if you take it out and you press a line again and you start it from a different attempt.
But the buttons on the left, they stay gray. I can't touch them.
That's because you're still inside the hole, so they automatically gray out once you're inside, so you need to get the peg back first and then press a line and take it from there.
Other way, backwards. Back. Thank you.
Yes, he's moving out, okay. So now the button should be enabled again. So he's having a tilt, a heavy tilt on the peg. So for those of you who tried, it's impossible to enter it because it's metal on metal. So the friction is very high and it actually jams when there's an angular offset. And it's quite tough because it's only 150 micrometers that he needs to align all the angles and all the positions of that peg. Okay. I think they're doing the photo shoots. So we're in the middle, so we still have 30 minutes for it. That should be fine.
19.
18?
19.
19.
Until the first soloist.
So what is he doing? Hmm? So Andy, did you align it again?
I just wanted to get a little bit closer to the hole because it's very hard to know, because of the delay, how far in and how far out you move every time.
Right, that is correct. In fact, you have to watch that icon on the pin on the vertical scale next to the video. But that's a good thing that he moves it close to the hole and he aligns it from there. Is much better than from the first distance where he did it. Well, this shows this is real. We are not staging this with some plastic or Delrin or Teflon pins. This is really metal on metal. And it's a tough thing to do. It took the guys in Deepwater Horizon about 6 months, I think, to fix the problem, which involved opening and closing nozzles. You're not running external mode, Eloise, are you? No.
So we can see it on the back.
Yeah. How is the alignment now? Still bad, he didn't align it, huh?
Just press pre-align, I guess.
Yeah.
If he goes in now, it should be okay.
Yeah. Okay, he moved it out again. And it's kind of a bit tapping in the dark here without the buttons.
He's going in.
All right, he's closing in. All right. See, I'll let him do it on his own. I don't want to intervene too much. Like on Mars, he would be on his own. He would watch the training video. So I'm allowed to talk a little bit.
So he didn't watch the training video that you sent.
No, there was no time in his mission to do that. So he's so full of experimentation that they shifted it to ground. He was supposed to watch it in Kazakhstan before his launch, but he didn't.
Not good.
Well, since the laser is gone, he's not too bad, but the best thing he would do the automatic pre-align. Andreas, you can also use the automatic align button multiple times, which can be a good help to get to a good starting pose.
If I press the line arm, it takes me all the way out to like 50 centimeters.
Right, it's about 10-15 centimeters from the taskboard, but you can press it multiple times and it will still fine align to it quite well. And then you can move closer and manually align with the laser and hammer it in. What's the stiffness on the arm? 200, 500?
The stiffness is 500.
500. That's pretty high. Okay, so he aligned the rotations. I think he's moving it in again, giving it another try. He's getting close to it. I think he got stopped. Still seems to be commanding it. There's some heavy delay going on here.
Nominal.
MPCC nominal?
Data rate going up, nominal.
Okay, he's closing in. He's at -20. Again, -24. I think he didn't realign that one. Or he can still move it in, and there's just a... How is the LOS?
11 minutes.
Okay, he's moving in, -30, -35, -38, and he's in. Okay, Andy, you reached the pack, you're inside the taskboard. So now you can see that the finish button is enabled, so if you press that one, you can finish the experiment. And we should see the gripper open once he presses that. Yes!
Yay.
Woo! And the connection is lost. Okay, let's reposition it. Andreas, so great. You actually managed, the pack is inside the hole. I didn't tell you before, but guess what the tolerance was on that task?
I think I read it 40 millimeters or something.
Well, actually, the tolerance between the pack and the hole was 150 micrometers only. So it was about a 1/6 of 1 millimeter.
Wow.
He's trying to calculate. What's a single millimeter? That's very small size.
So shall we try to do it another round? How do you feel? I would say we give it another try. I'll give you the go-ahead once we prepare the facility, and then in our next slot we'll do the other protocol one. But let's give this another try.
Got 10 minutes.
We got 10 minutes left.
Sounds good.
Great. So please stand by for 2 minutes.
No problem.
Is it okay?
Okay, can we put a camera, some photos from here? Then I'll tell him to wave in the camera. Andy, no reply required, but if you want to look into the camera, we'll take some pictures from ground, if you don't mind. Thanks a lot for that.
I wasn't sure if you could see me on the VCA camera or not.
Yeah, we can see you very well. It's a bit odd because our video is delayed and our voice is before. Great. Okay, so Eloise, on your command. Okay, so we give this another try. How long? What's the time?
We have now about 6
How long did
minutes.
it take? Now it took.
Took them a long time.
What's the time now?
44.
Everything's running.
Everything running?
Yeah.
Robot arm status?
Ready.
Ready? Okay, so we go ahead.
We took about.
Andy, we are ready to give it another try if you're ready.
I'm ready. Do I just start protocol 2 again?
Yes, indeed. So it took almost 50 minutes the first time. So the first time he did it, it took about 45 to 50 minutes. When we do this on ground, it takes about 20 minutes for us, or 15 minutes sometimes. It depends. The final alignment is very difficult. So now we consider this training because he hasn't received training before. So let's see for the second run how long it will take. And I leave him on his own. So that looks pretty good. He got the task boards. Okay, he registered the task board, so he'll start his drive. Okay, now we got the VR here on the ground, on his predictive display. So you're seeing here in yellow actually his current position, and in white what he's commanding. So because of the time delay, he gets a predictive commanding. And you'll see close to the taskboard some green squares that he needs to line up the rover with. Oh, he's moving much faster now.
No confidence.
Yeah, he's feeling already much more confident. Oh, it was started wrongly on the ground before. Wow, this looks awesome. It could be just right on the spot almost. Oh, it's a strange strategy. One more. Wow. That looks pretty good. Wow. Wow, he aligned it straight. Keep me on space to ground, please.
You're on space to ground.
Yeah. Andreas, this looks awesome.
So about 4 minutes.
So you see already you're enabled to go ahead. Great. No, not anymore.
Careful, watch peeping.
Wow, okay. He's aligned with the taskboard, so he's moving the robot arm right now. That was much faster. And he's moving the arm in on the target.
4 minutes.
That will be critical one, but let's see what he chooses to do next. So he's moving it by hand now, by incremental commands. How much time do we have?
3 minutes.
For LOS?
LOS, 3 minutes.
Yeah.
It's a 6-minute LOS.
Okay. And then we have how many minutes?
Until activity is over, probably 10. We have till 15:10 for the activity.
Yeah.
20 minutes total.
Okay, so he's choosing to do manual alignment of the robot arm rather than the automatic one. He seems to be enjoying the robot control. He can change the step size from 1 millimeter, 5 millimeter, and 10 millimeter steps, and the same on the rotations. He can change the degrees 1, 5, and more. So here you see the laser projected into the hole, which actually indicates that he's not well aligned. That's our way of getting. Who was that?
Just making sure they're not trying to call you to tell you LOS and things.
Yeah.
It's okay. Two minutes to LOS.
Okay. He's closing in on the taskboard, in fact. Well, this will give him force feedback. He's inside the...
Optionality is scored.
Okay, that's fine.
TC, go ahead. Yeah, would you be okay for me calling Kevin Passai on this loop? We need a message to get a message to the PI. Not a problem, Kevin, you're out there.
Yeah, I'll meet you on call cord 1.
He's closing in.
Then I got on call cord 1. Could you hint to Andre that he needs to hand over at the end of this KU path?
Copy.
I will.
Over now, 20 seconds.
Hand over now. Wait. Okay, hand over.
Andy, I will hand you over to Eurocom for we have KU out.
Copy that, Andre. Okay, Andy, this is Munich. We'll resume for now nominal space to ground. And I will have a couple of deltas for your timeline.
That's it, they're doing a PAO event next.
But we still have like
Okay,
10 minutes,
go
right?
ahead.
No, you're done for now.
So
Until
we
the
don't
next
need
protocol.
you to do anything with the equipment and interact because we will return very soon. So don't leave everything the way it is. So the next thing in your schedule is the PAO. You just go to that, and then the next one is skin suit activity. That small skin suit activity you can do as in the timeline, and the only delta is that at the end of that activity you may doff the skin suit and temp stow it. And then right after you have the rest again, obviously, you can come back to interact, please.
You're
Oh,
done
I see, I see.
You're done until later.
Okay.
Yeah, he'll come back. Okay.
Don't talk, don't push that.
Oh,
You're not
sorry.
you hand it over.
Not that I call Eric in the space station.
That's what I was just saying. You
Okay.
want to talk science? Go.
So, okay, he will need to do other tasks. It seems ground control decided. So we'll continue later with this one. We are now out of signal, LOS. So he'll go to some other assignment. We'll take off his suit, do some other experiments, and then come back. And we'll finish this one, and then we'll do the other protocol.
So we'll be back at 1650, according to.
1650?
Yes.
Okay. Eric, haptics or interact PI on ESA Science, are you there?
Yes, you can reach me here. I will have a meeting starting in 5 minutes though.
Yeah, can you briefly debrief me on the status of the sequence of the experiments? I'm a bit confused because we are still in protocol 2 time normally.
So, good evening, and this is Emil the Next here again. We're back for a little status update. We're just resetting because in maybe about an hour, we're going to continue with our first protocol, Protocol 1, which is our data collection experiment, where we'll have Andreas Mogensen use his joystick that is going to be synced up with a joystick, a similar joystick that we have here on Earth, and we'll have him probe different stiffnesses that we have set up for him on a setup right over there. We'll be switching cameras pretty soon to show you a couple close-ups of that thing. Just a wrap-up of our previous protocol. As you've all seen, the experiment was quite a success. We've had Andreas drive the rover around and find the task board twice, and the first time he actually completely succeeded in getting the pin in and releasing it. The second time, sadly, we ran just out of time in the last couple of minutes for him to completely insert it, but we're all very happy with the results, and in our eyes it was very much a success. So the next part, Protocol 1, we're going to have Andreas probe different stiffnesses. He's going to go through, well, hopefully to collect enough data, quite a few of these stiffness tasks. He might not like haptics so much after this experiment. Once we're all set up and we're ready to go, we'll switch our cameras to our new setup. You guys can watch along. Thanks for watching.
So this is the space part of the Interact Protocol 1 setup with the one-DOF and the tablet. And you see here behind the ground part of the experiment, which has the engineering model of the one-DOF and a spring simulator, a stiffness spring simulator here. So this device simulates varying stiffnesses of springs, which you can change in your stimulus. So let's log into the screen by homing on the Windows button and starting the Interact app. I'm going to use the first name of a famous astronaut here to enter. If you have a typo, you can use the backspace button or the clear and enter a 4-digit name. And I'm going to start protocol 1B, which is the object stiffness discrimination. You'll first get some introduction about the protocols and a sequence summary, but essentially the conduct is fairly simple. It is very similar to protocol 6 of the Haptics 1 experiment, with the only difference that now the stiffnesses are not rendered locally on the one-DOF, but actually remotely on Earth through teleoperation, and you're receiving force feedback on the stick. So right now the first stimulus is selected, A, and I can use this handlebar to actually control the slave unit to engage with the spring, which will give me force feedback here. And after unloading from the spring, I can select stimulus B. Stimulus B is set once the actual stimulus is highlighted in green. And you can again move and probe the second stimulus. And then decide which one has been the stiffer one of the two. And press next, which will move you to the next trial. So every trial is similar, and you can cycle through the number of trials which we will set on ground. In the beginning of the experiment, it will be about 120. Important to note is, once you press into the stimulus and you apply a force, if I now intend to change to B, the system will not allow me to do that. And it will be set back to A, so always the stimulus that is highlighted in green is the actual one that is set. I need to offload the joystick and swap to B. And now I can probe the level B. And I can select whether A or B is the stiffer one and press next. After you've completed the trials of the experiments, after testing your last pair, you again move next, which will finish the experiment automatically. Up here you have motor enable, which enables if the motor control is pressed, and teleoperation, which enables if the yellow start button is pressed as well. So if I do my last selection here, next will finish the protocol, which will move you back to the homing screen and allow you to retrieve the data via the memory stick. You see also that the increment of the trial has increased to 1, showing that one trial has been successfully completed.
Okay, test 1 2 1 2. Okay, this is Emil again. We're back just for a quick comment. It seems we've had some connection with the ISS and some contact with Andreas. He's still preparing for the next session of Interact Protocol 1. We're just waiting for status, and as far as I've heard, as soon as he's ready to go, as soon as he's finished taking off, I think it's a skin suit, we can start the next protocol, and then we'll switch to the next camera, and we'll also have live audio again. Thanks for watching.
That's easier to do repetitions on the
Copy that, thank you. If you are ready to start again, then I'll give you again to Rashid in Aztec.
That's Pedro. Wait. You get the
Okay, I'm ready to start again.
Okay.
Okay, haptic API, you'll go to take the loop.
Hi Andreas, this is Andre, Haptics PI, Interact PI on ground. Good to see you back in more comfortable clothing.
Yes, nice. Maybe it'll go better this time.
Right. We'll start actually with Interact again, and we'll redo Protocol 2 first. So we reposition the rover to its starting position. So don't look on the video because it's delayed. It's very confusing.
All right, copy that.
Comment go flight, I will...
I should not look to it because it makes my head.
Thank you.
So ground side is ready, and whenever you're ready, you can start the Interact app, log in, and start Protocol 2.
So right now I've got connection link was lost. Please wait until it's stable. How do I restart the app?
Restart the app.
This in the connection lost mode.
Is there a button called Resume?
I'm back on the protocols page now.
All right, from there you can select Protocol 2. Oh, he's connected.
Okay, I'm back now.
Right, enjoy the ride. He's in tool control. Why is he in tool control? Oh. Okay, Andreas, we see that you're in tool control on the space GUI. Can you confirm that?
I'm on arm control when I should be...
I'll tell him because he can't do anything right now because he's not getting communications a second. Hey guys.
Is the rover back at the starting point, or is it rover by the task board?
You lost your connections from the track connection.
In fact, I would like to ask you to select Stop Protocol because it's still open from the last time, and we have an issue here with the MPCC connection. So please press Stop Protocol and stand by for 1 minute.
I know. Just tell him to get on. Yeah, go ahead. Did you get the track connection back yet? Okay. Yeah, we're just checking out. Is that counting?
It's good.
Okay, confirm we're all good.
Okay. Okay, thank you.
Okay, thanks. Yeah, Peter.
Can we ping our onboard computer, Manuel?
Yeah, I'm just getting the models.
Okay, you're hard on the space to grounds again.
Let me know once you have a ping, then I get back to him. He's standing by still.
So it's trying to explain to you there's no connection.
Don't kill the models if they're running now. Wait. Yeah. Well, don't trust what you see here. Are the processes running or not? Now they're stopped. Okay. Hi, Andreas. This is Andre. So you can start the Protocol 2 from here. Still in tool control. Yeah, I think he's just starting it now.
It will probably change back.
Okay, he's got his video.
Yeah.
Is he moving the head? No. Is he still in tool control? Andreas, could you read back whether you're in tool control or in target finding mode?
I'm in tool control. It says tool control, and then I'm trying to move the camera head to find the target, but it doesn't. The camera head doesn't seem to be responding.
Do you see the stop protocol button? I don't read him.
He's not talking.
Andreas, can you see a stop protocol button in the GUI?
Do you want me to press it?
Yes, please press the stop protocol button.
Okay, both sides are stopped.
Okay, perfect. So now you should be back on the protocol selection screen. Oh, he already pressed start.
Yeah, that's what I had before, and when I selected protocol 2, then instead of starting it, it brought me back to the page where it said connection has been reestablished.
Our GUI is messed up. Why does it
With the
show
choice
tool
to
control
resume?
Can it be that he has started the application twice on the tablet? Can it be that he started the application twice on the tablet? I don't know.
Andreas, we're trying to debug the situation. Maybe it's best you entirely close the GUI on the tablet, and you do that by double-clicking on it and then using your finger on the red X to kill the application. And please inform us when the application is closed. Do not use the Windows button. You have to double-click and exit in the window frame on the screen. What's that?
It's Andrea. It's Andy, not Andreas. Andy.
Yeah. It's called Andreas Mogensen, isn't it?
They call him Andy.
Yeah. Okay, I think he stopped it. Can you see, Manuel, whether he stopped all the processes on the wand-off? Okay, and he's restarting it. He's doing what he's not asked to do. You see target finder, okay. You should be fine. I'm seeing the target finder window here on ground. Please read back.
That's affirmative. I got target finder.
Okay, so we are good to go. And I
moving.
see that you pan around with the camera. Okay, so he has control of the camera right now. He's looking around. You see his video feed, what he sees actually here on that screen. So he's scanning the environment now to look for the taskboard. And since we did that one more time before, he knows where the taskboard is by now.
A lot less latency, it looks like, Andre.
Andy, I hope you saw the footprints in your first video shop.
Yes, I saw the footprints.
Wasn't me. Okay. So his task now is to line up the crosshair actually with the taskboard and then register this place target, which will then register the target in the compass view that you have here, which is basically the compass of the entire experiment, where the rover is heading compared to north, south, east and west. So once he places target, there's this target symbol placed, and the camera now zooms back to driving mode, and from there on he will be enabled to just drive freely with the hardware. And he knows he has to drive to the left now. How is KU forward? How far?
We're doing pretty good.
KU
we have
LOS?
in about another...
Oh, a lot of time, right?
So your activity's done.
Yeah.
We're safe.
So here's the augmented reality overlay in the camera stream. So these yellow dots show his actual situation, and the white ones is what he's commanding. So he's commanding, and because there's a time delay, there's a predictive display, and then it always lines up again with the... so you see it better when he goes straight forward. He sends a command, and then the robot drives, so they align. And near the taskboard, we have placed a green marker where he needs to park, because he needs to park with a very good precision in front of the taskboard in order to have reachability of the robot arm for the pack-and-hold task.
Is that programmed in, or would that look at the run? Is that programmed in, or if he selects a different target, does that work?
Now we have only one target, but the idea is if there are multiple targets, each target has its optimal parking spot, and that can be identified automatically from the manipulability of the arm, for example, and locate him optimally to do manipulation on the taskboard. So he doesn't need to know the singularities and all the workspace of the arm and so on. So this is a way for non-robotic experts to actually do these operations in a very intuitive way. And we're actually completely hands-off now from the robot. Like, raise your hands, guys.
Reach for the sky.
Can you take pictures as well?
Yeah, of course. So his task now is to align, and there's a quite strict requirement on angular alignment. And he has found his own strategy, I see already, on how to align it. He aligned it now spot on, actually. Joao, you might want to look at where's Joao? Oh yeah, you're there. Good, thanks. He's doing excellent, actually. But now he has a too large rotational alignment. Now he's fine. And you see that this next button is now enabled, actually, so he could press it. He couldn't press next before he was aligned. So this way we automatically guide him. He already starts aligning the robot arm. He's moving it fast this time. Wow. Did we stop the time?
Yes, I logged it.
Yeah? Thanks.
3 minutes. 3 sorted.
Can you please write the start and stop time here?
Everyone logged it.
Yeah. It's pre-aligned by the robot, but it's not perfect because the accuracy is sub-millimeter, so he has to manually fine adjust it and then insert it with force feedback. Now you see that there's a laser spot that is projected on the taskboard that you see here. And when the laser disappears, it's already a sign that there's a good alignment in over the hole. There is no. The joystick is for the Z-axis, and he's using a widget in the tablet screen to control all the other degrees of freedom. So you're doing extremely well here. What was the starting time? Oh yeah,
15:50.
Okay.
4 minutes in.
Yeah. And he swapped to the tool camera, so he can change the camera feeds. Now he's looking from the camera that is mounted to the gripper. And probably he'll start looking back and forth in the head camera and the tool camera to work out the alignment. It's super difficult, actually. And now he's starting to close in on the target, actually. You see that the peg is moving here down, so he's already inside the hole by 10 millimeters. And of course now it's a question of the angular misalignment, whether he can put it up to the -40, which is where the target is. So if he succeeds here, a lamp will go on, and the finish button enables automatically. He really does enjoy this. I don't have the banana in you. So the laser is a way to not need stereo vision. Okay, he's closing in. -30, he's really fast now. I think if he succeeds now, it's a super fast run. So still 1 centimeter to go. But I think he received force feedback, so he's still too much misaligned. And he's moving back, I think.
Yep.
Yes. This is extremely difficult because there's now actually intentionally not a lot of light on the taskboard because we want to make it as realistic as possible. And it's really a sub-millimeter tolerance that he has to align angular, and the peg is actually 14 centimeters long. So if there's the tiniest misalignment, the radial tolerance is only 150 microns. And it's metal on metal. You can try later on the taskboard. If you just misalign it by hand, it's impossible to insert it. And he has a distance of 144,000 kilometers that the signals travel at the moment. Up to geostationary orbit, down to the robot, down to the US, from the US here, and all the way back. 36,000 kilometer altitude. Okay, minus 30. Uh-oh. Did he get the force feedback up there? No?
Yeah.
Now,
Can
now,
we see somewhere the force?
minus 30. Hmm?
Can we see somewhere the force?
Not now, no, he only feels it. Andreas, since you haven't seen the video, in fact what you can do once the pack is outside the hole, you can also press align 2 or 3 times to get a very good pre-alignment the first shot. Okay, he heard my comment. Okay, fair enough. A small video sequence from here, just from here, like from here. Yeah, just from here with my phone. Like, look, this shot. Just the TV and the world. Yeah, so he's pulling it out now and doing a pre-align routine again to realign it multiple times and then insert it again. It is very difficult because, of course, as you see, the visual feedback is limited, and maybe in the future we will need more features, actually like virtual features, like for the overlay, like for the driving, also for these type of tasks. Yeah. Yeah. Our exoskeleton ultimately. Yeah.
They have 100 and they got the back to 1.
So he's giving it a second attempt from the start, and you can see that there's that the laser spot still is sometimes visible, which means his alignment is medium good. Without the laser in the tool, it would be nearly impossible to do this task. And without the impedance control on the arms and the force feedback to the stick.
And it's only one laser pointer?
Yeah. No, it's only one actually, which is used for the spatial information, for the depth, for the. So you know basically the contact point on the work site from the tool. Yes. We actually we didn't have the time to do that. We wanted to have a virtual geometry like a square that deforms based on the angular misalignments. So for the actual, so he's closing in minus 30 now. I think it's gonna be in. Yes. 40, okay, finish enables, lamp will go on, lamp is on, yes. He made it. Okay, great. Andreas, you made it. 10 minutes. 10 minutes. What's the time? Exactly. What's the time? 7:01. Okay, so let's set it back and let's swap to protocol 1. How difficult was that, Andreas? Oh yeah. You still need to press the finish button, which will release the gripper on the ground. Yes, there you go. Okay.
The first time was definitely the most difficult, also because it had the longest delay time. The delay to get shorter on the.
Right, you did extremely well. The first time you took about 45 minutes, but then we talked a lot through the assignment. Now you completed the task in as little as 10 minutes. It's not the
But
most.
I mean, man, took at least 10 seconds before I could see any response on the video here.
Right, we need to look into what the cause of that delay was. It was very high, I think so as well, because your actions were even delayed longer than the video stream from the Columbus module. Jan, we're setting up protocol 1. So now we are actually preparing for a different protocol, and we'll see how far we will get in it. It's protocol 1B, which has to do with stiffness discrimination. It's very much like the protocol 6 on haptics 1 that you've been trained for.
All right, should I go ahead and select protocol 1B?
Yes, please. Are we good? On my mark. Wait, is it good or not? No. But it doesn't matter if he starts it already, right?
It does.
It does?
The camera's not showing. It should be okay.
So what's our time? Can you show me the time? We got like 45 minutes? Okay.
47.
So Andreas, while we are preparing the setup on ground for protocol 1B, we have about 45 minutes left. Probably it wouldn't be sufficient to run through the entire protocol, but we'll just see how far we can get and get a couple of samples, get you used to the task.
Right.
We are preparing the ground setup here, so you can stand by for 2 minutes.
Sure, no problem.
What? Kernel problem?
No problem.
Oh, kernel problem.
Panic.
Kernel panic. Oh. It's now good? Okay. Let's give him a 1 minute breaker. Okay. So while we are reading here on ground, the task on protocol 1B is that you probe different springs here on ground, remote controlled with your joystick, and you'll be presented by 2 pairs, A and B, and you need to select which one of each pair is the stiffer one. And
Like the stiffer one.
right, you'll see that in the GUI once it is up, and there is about 120 trials actually in this protocol. It's a rather lengthy protocol, but we'll just see how you go through it, and after the first 30 we'll make a small break.
Okay, sounds good.
So we are ready when you're ready.
I'm ready.
So we'll ask you to start protocol 1B.
Go ahead.
Connection.
I have to check with comment for my image 1.
Who is that?
Co-flight.
Okay. So connection is there. Teleoperation is not there. There is a couple of procedural things on this experiment that I would like to talk you through. No need to reply. The joystick first needs to align to the ground joystick. You're seeing the ground joystick in the video. Let me just say hi to you. So in this ground joystick, you will move this with your joystick, and this joystick here will simulate different springs. So the first thing that will happen is your space joystick will align to the ground joystick. So you have to comply, and then you're in control. So whenever you're ready, we can go into the first trial.
All right, I'm ready.
All right, let's go.
Who's the spring man?
The spring is automated in the meantime. Okay, so he's moving the joystick. Okay, good. Okay. He let it go, huh? Yeah. And it's also sufficient to press it slightly. You don't have to put your entire force into it. Okay, it's nodding. Okay, that looks better. That looks better. And that was B. Okay. Can someone, Nikki, you're very good at writing down stimulus levels.
Yes, I am.
Can you write down the last one he selected, just as a double check, that we, if we have to interrupt, we know where to start. And the trial number, please.
You can see in your view.
Yeah. That's stimulus B. So he's checking, I'm not telling that to him, he's checking the 40% difference thresholds right now. He moved on to the second one, which means there's always a reference stimulus, which is exactly 1 Newton meter per degree, per rad, and per degree, thanks. And there's a reference and then 40%, and they are randomized, and we repeat throughout the 120 trials multiple sets of these randomized comparisons. So we are testing actually 4 difference levels: 40%, 25%, 15%, and 5%. So everyone is tested actually 30 times, and we see how many times he has it correct. So we get the statistic whether he's guessing or not. And if we assume, for example, 90% correct answers, then we are sure he actually perceives the difference. And while it goes smaller, this curve actually settles down, and 5% will be very hard to perceive. So with this, we see exactly in a psychometric curve where his perception threshold lies for that reference stimulus. And we did the same measurement in haptics 1 in space with a different crew member though. So we know what is the contribution of the microgravity and what is the contribution actually of the teleoperation. So ideally, we will redo this experiment with the same crew member that will do haptics 1 and this one. Then we know exactly what is going on in space and due to the teleoperation. Okay, that sounds interesting. So for us, it's now just waiting, and it's quite a lot of trials that he has to do. He's now in trial number 3. Usually with time, it will go faster. John is making sure Andreas Mogensen sees him on the video stream. No jokes about astronauts in the video stream. Okay. Wow.
Slot machines in Vegas.
Yeah. I hope some money will fall out for our next experiment.
You have to put some in first.
Oh, we have our money donated here.
You look at the fruits of what you put.
Yeah.
What is actually deciding? Does he do it twice? One is different than the other one?
He can choose as much as he wants between A and B, and then he chooses which one is stiffer and he moves on. And they're randomized, so it's never the same repetitions of the same A and B.
The first presses the A or the B, and does it.
Yeah. And then selects which one and moves on. So it's actually double-blinded. So we don't know what he's selecting, and he doesn't know what he's selecting, and we see absolute truth in the measurement. Whether he actually guesses, then his guessing level is at 50%, or whether he actually knows, which is then above 75%.
How much is the difference? So one of those would be a 40 and the other a 25?
At the reference. So there's always like a constant stimulus, and then the differences, the second trial varies around this, and they get smaller. So now it's still at the 40% level. I coincidentally know that. He doesn't know that.
So 40% stiffer or less stiffer?
Yeah.
One of the two.
Both, yeah. So this will take a while. Let me see, how far are we from LOS?
We'll go quite a ways. Till the activity is done, that's it.
Okay.
Well, but your activity is going to be done at 17:45, remember? Hard cut.
And now
30, you get 32 minutes.
He won't be able to complete it in this time frame, but it's okay. We at least collect as much data as we can. And we have retrieved the log on the second protocol 2 run.
From space?
From ground.
From ground.
Yeah. Manu will collect it on the second. All the logs to space in the ground. And if you want to retrieve the space log, or is it too dangerous now? Maybe we do it later. We do that with the normal signal downlink. And what was the problem with MPCC losing connectivity? And they haven't prepared it or?
No, we get it.
You know, we should just use the normal track system. just adding complexity to.
Oh my god.
Eurocom STM flies on support for your information. Microbial swap is grayed out by Andy. No need to call.
What? Nothing.
Spinning concursion.
I'm wondering if that
It's moving slow. But he's very careful, that's good. Better he's careful than sloppy.
Maybe you
We don't get that much chances. This protocol, if you would finish it, would take 1 hour normally. So I think in this speed it will take a bit longer.
How much time do you have?
I saw things happen.
He has, for this one, he has less time allocated. Actually 35 minutes were allocated initially. But he also wasn't trained to any of the protocols. So we had to, the OBT videos, which they wanted him to watch in Kazakhstan, he didn't watch.
Andre on Space Now 3.
Yes, Andy, go ahead, I'm here.
So all this is quite difficult because it seems like sometimes there's a lot of play in the joystick. Like sometimes I can move it quite far before any resistance is felt, and other times on the same one, like the resistance is felt immediately, even though I'm starting from the vertical position in both cases.
That's correct. That's due to the control method that we use. So if you use the joystick in a slower, it will move less far than when you move the joystick faster. So it's actually sort of rate control also here. Yeah. We never did it through teleoperation. Kimiya Yui did it with actual springs. So we had a couple of comparisons from him, but we never used it like in this automated fashion. And the time delay makes it, of course, very hard. We didn't know the precise time delay, of course, before haptics 2. So now we know. And this time delay makes the whole task a bit difficult because he's actually setting this stimulus. So he's selecting which stiffness to test in space. This information goes via the satellite up to this system here on top, which renders the stiffness. And then it informs the space part that he can actually probe. So we're losing a lot of time really in communication time delay here. Which is why he can't do like haptics 1, just goes through and tap one after the other.
I think I'd be concerned about one that could be too boring if you do the whole hour. Maybe if you have to push all the time, maybe fatigue affects the...
Oh, there's not much fatigue effect there. It is a bit mentally demanding, so we do breaks after 30, and now he has to get used to it because he hadn't had the training. So after a while he will be faster.
The fitness depends on range. Now you have to incorporate this information to ensure that he has the same range.
Yeah, exactly. And he's learning very fast, and we could see that with Protocol 2. I mean, he had a 400 times improvement on the execution time from one trial to the next. It took 45 minutes and then just barely 10 minutes. And I'm sure next time he would do it in 7, and then probably it would settle in, like in the time we used to do this experiment. But normally all of us, we have done that like 1 or 2 times, and then we are more fast. But if you never did it before, this is difficult. So we had estimated this time like from 35 minutes to 1 hour. And then on the other side, today we got like replanned multiple times, and he hasn't seen the video, so we are kind of even. We agreed with the science office. So we'll do a retest of this experiment actually with Yui to do a full run. Because we had allocated multiple hours today, but then the astronaut chose to do something else, in fact. So he disappeared from the space-to-ground loop suddenly.
He does everything eyes open, or does he have different perception?
He has the eyes open in this case, because also haptics 1 we do eyes open, so he gets a little bit of position feedback on his hand as well. Wow. Okay, now he's hitting it hard time. Sounds worse than it is.
Will all the astronauts do?
SDM flight comment on ESA 4.
Unfortunately
If you have a
not.
minute.
Who did they call?
No, this it's
No?
flight 2.
No. No, haptics 1, we have 5 astronauts who will do it, but that's not via teleoperations. And he mainly does the rover drive and it.
But just checking before I issue the request to Opsrun, we shall remove the blue sequence of the task list of Mogensen, all the task lists, so we'll never use the blue sequence anymore. Is that correct?
They just took away all his task
Give me a
list
second.
items because
Yes.
he's
We have,
two by the books.
yeah, we have the scripts. We will have the scripts today.
Following it really exactly by the timeline. He didn't
The
deviate.
split about in
Also
seconds.
what he said. Doesn't matter. No, he was supposed to deviate, but he didn't.
Oh, I see.
Because they wanted to start you first. We had to
What was that? Please don't make such sounds that sound like breaking the joystick. How are you doing up there, Andreas? Do you perceive some differences? Just a general question. Oh, connection loss. What is this? Are we in LOS? Handover?
Micro LOS.
Ah.
TDRS handovers.
So luckily our software is robust to LOS. That one was unexpected.
In fact, you can't talk to him because he's on the KU band.
So, but isn't Space to Ground 3 normally S-band?
No.
It's 4.
We had 4 of these.
It's coming back.
What happens if you pick up?
He basically, once the signal is there, this one turns green and this one as well, and he can click resume and then everything starts gracefully again.
Yeah, that's such a small LOS. How do you see that?
It will.
20 seconds to complete just a handover. We have the S-band back.
Maybe let's go, yeah.
Sometimes it takes longer to
You can talk a little bit.
Is that you? Is that you? Okay. We're back.
Okay, we're back. All right, so still works? Yeah. He's a bit on the slow end. Where's my book?
Over there.
Oh yeah. He's checking his timeline now. We should at least complete 30. Andreas, Interact PI on Space to Ground 3. We are back. LOS is over. How are you doing up there?
Good. It's difficult, I think, to determine the stiffness between the springs, but otherwise it's going well.
All right. Do you have the impression that sometimes you're perceiving some differences? You can just nod or shake your head as well.
Sometimes, but a lot of times I think it's also, I guess, it's very difficult on some of them.
All right, that's very good to know. We'll at least progress up to the trial number 30, and then we'll see how much time we have left on the timeline. We'll be watching the timeline for you from ground.
It's always the same, isn't it, though?
Yeah, it doesn't move, right? Is it stuck or something?
No, the stiffness.
No, it's varying, like left and right and
No,
plus
but
or
it's
minus.
always 40%, isn't it?
Yeah, up or down.
Yeah.
Auto reference, so there's 3 different levels now in these first sequences. And then they narrows in like smaller. But it's now exactly the same levels than haptics 1, which has the merits of comparability, of course, with haptics 1. But it's difficult. It's already for non-tail operation actually difficult. So for a normal human like me or you, it would be around 20% more or less, where it stops being discriminatable. And in the in-flight data of Wilmore showed that it's actually getting slightly better for Wilmore, or he had a significantly better day. That's why we need other astronaut data. And here it's the same levels through tail operation via 150, almost 1,000 kilometers, so it's extreme. I mean, there are only very few control methods that can do this at all, in fact. So we saw in the test that we did here that it's still perceivable up to more or less the same range. But of course in the space environment, and he is not adapted to the space environment, so he just arrived 2 days ago, so that makes it much more difficult, even for him. So I think after 30 I will cut it here and then have him rather do another task on the robot, and then we close it for today.
Andrea, maybe you should mention that stiffness is going to change when he's still in contact with the
Oh yeah, I didn't mention that. Thanks a lot. Yeah, Andreas, no reply required. Actually, these stiffness levels cannot change when you're still in contact with the spring. I forgot to tell you that. That wasn't a training video.
We have to make sure that he actually, that's going. And can you see it? Can you see this image?
Yeah, he sees the same videos. He sees, in this experiment, he sees exactly what we see. In fact, so if you see now there's contact and there's already inside the contact. So there's the time delay also between the two. So shall we give him another rover ride after 30 trials? But this one is not collected, or are we only recording the video here? But here we only record data once he presses the button. Jan, do you have a second?
Because now we're at 100, but we only have 60 megabyte left.
But it locks only the answers here in space. When you press me. So how much space do you have? 60 megabytes. And since it started, we have something long. Okay, then we stop definitely at 30. The copy to the tablet? Yeah. But let me know when it's getting critical, then I will cut it.
Should we start with a different start or then or not? Should we start with a different starting?
Yeah. Let's face him here when we start.
You got about 15 minutes.
Protocol 2, we do protocol 2. We only do 30 trials and then we do protocol 2 again.
But it was not very I don't know if you recall, but we wanted to have this, to be sure that we are in space, showing this difference. We asked for this. No, here we are doing the discrimination.
15 minutes.
Okay.
PMC.
Okay. 22
Is it
trials.
22?
Okay.
Okay, so
Still 8 trials. Okay, let's prepare the robot. Actually change the starting condition a bit, so he looks, I don't know, looks to us, or or is it tricky with the mic on? Just let him look to us this time. What? Yeah, sure. Andreas, no reply required. We are already preparing the rover for you for another run after trial 30 as a small, nice close down of Interact. So each time you hear the loud beep, it's either that I press this button or he presses his button. So it's on the space to ground comms. If somebody from space talks, you hear this beep so that you pay attention to what they say. Whereas all the other loops, they don't have that beep. Quindar. But you switched off this one?
Then when we talk to Andy about EPO, we tell him he has 3 EPO scripts on the task list. That the other priority is Lego, then CubeSat, then robotics, and that in order to save time, we would like to perform everything in Columbus, where the setup is already fully ready or partially complete. Yeah, and prioritize-wise, I think it's robotics before CubeSat. CubeSat is lowest priority.
Robotics is you,
okay,
right? Matter on or not?
Just execute by this script. Is this correct understanding?
They're having it about robotics objectives.
That's correct understanding. Okay. They make it easier just by this script. You can.
Oh yeah. You have 2 times,
and
2 hours.
I can confirm the priority. Now make mention. Okay, I'm not sure what you mean by the scripts, because I mean you have 3 scripts in the negative. It's a single script. It's attached to all the messages. One script contains all EPO scripts. Single script, if he executes this from top to bottom, he will do the scripts in the right sequence. Just one setup and 3 different things.
Did someone log the starting time for this protocol? Yeah, what was it?
In other words, from the task list, he can pick any of the task lists, an EPO script, he will guide him to that script, and if he executes that script, begin to end, that's it. Okay. And to come back to the camera settings, we direct him to a procedure, and according to Photo TV from NASA, this is HD setup with the user standard, and the user standard for all their PAO and EPO activities, so it should be HD if he follows the procedure for the setup. Okay, I understand, but I was told it was not the case at the first attempt, so without getting system too much on it, I think we can...
That's more data-friendly.
Call and maybe send him to the activity, we can just remind him that camera should be set up in HD. Yeah, first. Camera first.
Should have asked him to wear his patch. Oh, he's wearing his patch. Is that the Interact patch?
Go ahead.
Maybe another clarification.
It looks like the
after the
internet.
private medical conference, we have changed in the evenings by intention because we have band coverage, KU S-band. And if you want to do this still, we would prefer once we have good KU at the end. So that's why we put the down step 7, the downlink there.
Okay, I understand. That makes sense. You want to protect between Pred for other reasons? Because if not, I was wondering we could send Andy to EPO right after.
Asking for a photo pulse.
I wouldn't say that.
Okay, 30. Did you see the selection?
Okay.
Hey. Hi Andy, so we saw you completed trial number 30. Just something off the record, do I see the Interact sticker on your t-shirt?
No.
Yeah, right, I meant this one. I was wondering whether you would stick on the sticker, the Interact sticker that you were given to bring on board.
No. What? You don't know where it is.
You didn't off-gas it.
All right, I see. Okay, okay. We'll do that for the next experiment we'll jointly do together.
Yeah, yeah. That has to be approved by the Russians to go up on Soyuz a few weeks before.
Timeline, please.
Yes. Timeline you have.
Right. Okay, Andreas, so
11
here's the deal.
minutes.
We have only 11 minutes left. Do you want to give another shot on the rover? Then you would need to press stop protocol and we'll set up the rover for you so you can try like a super fast action on the rover.
Sure.
Great. You only need to press stop protocol so we can start setting up on ground. And we got it from here. So stand by for 2 minutes, please. Okay, let's start. Data full. Okay, copy. And then we'll set up the new one. And it's deleting, it's not deleting it from the notice. Yes. After it's copied. Because you can't read it. No, it moves it when it deletes it.
Atomic profile. Go ahead. Yeah, can you summarize me that report from Andy? So where we at with protocol 1B? I understand you want to switch back to protocol 2, but what did you accomplish with 1B?
The PI made the agreement to do 30 runs and then switch to protocol 2 again.
Damek PI on call code 1.
Go ahead.
We actually did about 25% of the protocol. He moved very slow through it, so I decided to change and do one more run on 2, and then we are done for today.
Copy.
Yeah. Ready,
Ready?
Yeah.
All green?
All green.
Okay, Andreas, the robot is ready for you, now starting in a very different position. So if you want to start protocol 2 for a last time, you can give it a shot. Let's see if he remembers where the taskboard is.
Everybody wait.
Cold plate ECB need for PMC.
Go ahead.
Yes, we have confirmed a good end-to-end test with our ISSCB counterparts. We have our surgeon in the PMC booth, so we are all ready to go.
Yes, good. That's for the.
Can you give me a 2 minutes before?
Absolutely. You know it now.
Okay, registered the dashboard. Now driving into the operation station.
Is it going to be just a roll? Take us all out.
Just yeah, it takes us all out, exactly. Oh, he's moving away?
No.
Did they do the pictures, the high resolution photographs?
Yeah, I think they were taking
What's that?
postcards. Postcards.
Postcards?
Yes.
Now?
Oh yeah, airmail. You gotta get it out in time.
I could do a joke, but I will not do a joke.
Let him focus.
Because he's not talking now, he's reading his mail.
That's for his private medical conference.
Yes,
Oh,
he
right.
would like to comment on his accord.
Oh yeah. Oh, that was easy.
How's he supposed to drive up on top of the green dots now?
Okay, so he scaled down now the increments for the commanding. You don't see that here, but he has buttons where he scales the command. Yeah. Oh, that could be fine. Could maybe be fine.
That's a cool little
So Andre, on Space Ground 3, I don't have the little yellow and green targets as before.
Oh, we see them here on the ground GUI. That's not a good sign. I think if you try 0.1 forward, let's see if you can enable the next button. Why not?
Yeah, but he can't see it.
Okay. And perhaps you can change to the tool cam view and back to the head cam view to see if they pop in back in place. Do you see them?
So there's no target or prediction.
How come the please stand by. How come we are seeing this on ground?
You got 5 minutes.
Yeah. Can we start the Y constant or? Yeah, go ahead. Maybe someone touched the cameras. No?
That would be a local problem with the
Uh-huh.
Maybe you can guide him?
No.
We can restart it. At that point.
Yeah.
4 minutes.
Andreas, I think it is better to restart if you press stop protocol and you restart the protocol and you skip the searching for the target up to the tool control.
Yeah.
He already started it. Maybe he started it before us. No, he didn't.
I do think he has to restart
The whole GUI?
Yes. It's doesn't make
Oh, we have only 4 minutes left. Then I rather give back. Won't
3
be
minutes.
possible. 3 minutes. Let's see. Let's see if it's there. If not, we cut it.
Give the guys a little bit of time, then we have it.
You can go skip.
Yeah.
Oh. Is he at tool control now?
Yeah, he restarted.
But he can't be at the tool control.
No, he skipped all the way to 2 control, as you said.
Andreas, Andre on Space to Ground 3, can you see the... no, you can't see them, I assume. Okay, we cut it from here. Yeah.
Time's up.
Right.
All right, we only have 3 minutes left, so we actually need to hand over to Eurocom and we'll stop our test here. We'll see if we get another slot during your flight to redo that experiment, perhaps in the next days. Thanks a lot for your help, Andreas. It was nice doing this together. Looking forward to have you back safely. Have a nice stay up there.
Thanks, you too.
See you at this week.
Bye.
Giving up at this point.
Yeah, you can tell.
Yeah, you ran into some problems with his offer, so I think it would take too long time to go out and
So this is Emil from the Telerobotics Lab here with Andre Sheila. We're going to sign off today.
Hi there. Well, thanks for watching, first of all. And we saw a lot of activity on the live streams. We hope that you enjoyed it, that you liked it, that you made fun, and you saw what we are doing. So we actually close it for today. We have achieved basically our Protocol 2 objective of the pack and hold placement successfully multiple times today. So we have repeated it, we have consolidated our experiment findings, and we have done a very brief run on Protocol 1, but due to scheduling constraints, we'll have to repeat that with another crew member after the SDM, which is also good. So very likely Kimiya Yui will be conducting Protocol 1 of Interact in the next couple of weeks. So stay tuned and follow us if you like. We are also on Twitter. We haven't been tweeting so fast, so much in the last time because we've been busy developing space robots.
That's it. Thank you very much, Andre.
Thank you.
So, everybody visit esa-telerobotics.net for more information on all of our projects and our upcoming live streams, hopefully, for our next experiments. We hope to live stream them all. And we'll see you guys soon. Thank you very much.